slow. Today, first I'm going to make some golden monkey tea with milk and honey, because we know how good that is. And then, there is a gameplay feature that we were not sure for a long time if we were going to do. We have enough gameplay features in this game. It's a huge game. But we were talking on Tuesday about how to lay out the overworld and what to do there. And we were like, well, we kind of want to do this thing, because if we don't do this thing, we won't be able to make the overworld as good. And so we're going to do this thing. And I'm going to see if I can do it all tonight. We've been having good fortune lately in terms of being able to implement entire things in one stream. The mega spoiler is real. If you don't want to know something cool about this game, don't watch. You're stuck with ERP and business software development? No, you're not. Quit and get a different job. Dude, people who can program 3D rendering engines make way more money now than they ever used to. Are you kidding? Anyway, as soon as the water is ready, which it may be, okay, we've got boiling water. We've got the teapot. We've got Winnie the Pooh. We've got milk. What I do not have is a spoon. Some say there is no spoon, but I have it right here. Okay. Okay. You used to live in a part of the world where 3D rendering engine programming doesn't pay the bills. Dude, you can get a remote job for some game company for like hundreds of thousands of dollars a year if you're good at it. Like no troll. No troll. Doesn't matter what country you live in. All right, so that's there. That's there. Now, so this feature, if you are prepared, everything I say from now on is going to be a mega spoiler. You know what? I could even show you. So, in this game, we have the whole point of the game is we have all sorts of different game mechanics, right? In different places, and we bring them together. And then the way the overworld is laid out, it's organized by game mechanic, right? And so you go to a certain part of the overworld, and that's where certain categories of puzzles are. I don't know why this is taking so long to start up, but you go to a certain part of the overworld, and you know, well, we can't see that far here because we haven't gone very far, but you know, these different directions, you can see how sort of on the east is islands, and in the southeast there's lily pads and all that, right? It's organized by topic. One of the problems that we have with laying out the overworld is that one of the sets of topics is character abilities. Here's the warrior, he could push a lot of things. Here's the thief, she could pull things, right? Here's the wizard, he could teleport. And because you're a different character than any of those on the overworld, you don't have character abilities. So we can't actually create puzzles that involve character abilities. And this is very limiting. It is, shall we say, a bummer. And so what I'm going to implement is our idea for how to do character abilities on the overworld. And let me just check. Oh man, we got a shader problem. Although I didn't really recompile the game, so it's an old executable. Let me just check really fast that we can, yeah. So I can change the color of her cape here. Right? See this? I could sort of, oh, if I select her. Right? And we don't, so the idea is going to be, fictionally, there's like little wardrobes going on with clothing items from these different characters, okay? And you walk through it in one direction and you like put on those clothes and you could do the thing, right? And then you walk back in the other direction and you take it off. And you know, we obviously don't have the art done for that, but each character has a color, right? And so we can visually signal in this temporary version of it. Like if you walk through the warrior wardrobe, we could turn her cape red, right? If you walk through the, you know, the wizard wardrobe, it's like blue. For the thief, it's green, and so forth, right? Okay. So that's the idea. I'm not really going to try to design any puzzles for this yet. Let me make a new release build. And we could start typing code. Oh, you know what? We're not going to be using release build very much because we're going to be, yeah. Okay, anyway. So I'm going to make a new thing. This is going to be called wardrobe. I don't have a better name for it. It's not really a wardrobe because it doesn't have a bunch of clothings in it. But anyway, we could actually, yeah, no. All right. So is literally it. Oh, so so here we have skill flags already. And what skills does this wardrobe add or remove? And really, it's going to be one flag at a time, unless we go bananas. Even if, no, because it's probably still one at a time. Cloak closet. Well, I don't know if it's a cloak, because it could be like a hat or little boots. What if we want you to have multiple? What if we want you to have multiple? Anyway. So when we, so we also don't have a mesh for what these will look like in the world. But I think they're going to be like fences. So it's going to be like one of these. So I think we're going to take this mesh for now. And that's just going to be what it looks like. Although, can I just change? Is this one? Do we have bent? Get bent. Okay, that's not very good. That's like what happens after you... Oh, maybe it's just sticking in the thing. No. Not appropriate. So we're just going to leave this, and we as developers are just going to have to know that you can walk through that, even though it looks like solid bars, and later we'll make the art for it. So, entity, editor, entity defaults. So this is what the default mesh is. I think for now, these are going to be totally... Maybe it's fine. We're probably going to have visual stuff on it or whatever, so we'll put it down there. Now, we're going to want to be able to ask, are you passing between this? So here we go. We're going to do cowabunga-oriented programming. All right. So we want a corresponding right? It's, I guess, which overload was it? The position in delta. Okay. So I'm going to factor these out. This could be any entity and any entity. Okay. Now, I want to make this generic sized, but first I'm going to pour my tea. Remember the tea, everybody? Remember that? Hell yeah, you do. Remember that I talked about honey? That's happening. That is happening. We're going to go for Bjorn's cinnamon Colorado honey. Hell yeah, that's going in there. To taste, which means a lot of honey. Whenever you see that in the cookbook, to taste, it means put a hell of a lot in. They don't say that, but that's what it means. That's what I learned anyway when I read cookbooks. Okay. And a splash of milk, and now we're good. Okay. So, cowabunga-oriented programming is going to happen. Now, this actually could go here. I'm going to say is fence-like between manager a delta. All right. And $, T is a type. We're going to pass that type as fence, and anywhere in here where we have, oh, this is fence like between, anywhere in here where we have fence, we're going to say T, 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 because the thing is, it could be in like either square. All right. And this is a pointer to T. Let's make sure that still compiles. Is floor fence between? What? Oh, I put the fence in the wrong place. I meant there. Is wardrobe between. Okay, so I just want to make an is wardrobe between, and we're just making little stub functions that don't do a lot. I just wanted to have this early out, and the thing is, this array is not very easily tied to the type. You could call a function to get the array, but that's a little bit slow, and it's like, why even do that? And then we don't even need this check. So this is like this. And we're just going to inline this puppy. Okay, blocking. If T is equal to fence, Because, see, this is one of these things. Object-oriented people think that, like, oh my God, as soon as you could pass more than one type to this thing, then it needs to have a method about, should I reject this thing from the for loop because it's different per thing? And it's like, nah, you don't need to do that. Just like, look, if we're talking about a fence, do this, otherwise don't. Like, that's just how it goes, guys. All right. Okay, so I actually want to make a level where we can just load it up real fast. So one of these, I don't know. Let me just see. I just want to grab one of these old levels and just take it over. I do that all the time. No, okay, that's not. Oh. All right, this one's fine. Okay. So we could have fun later and go through a fence on a lily pad. We'll leave one there for that reason. But for now, we're going to delete this. Going to delete these. Why can't I select these particles? Kill it. I don't know why that appeared there. Let's close that. Oh, shoot. I screwed up. I just deleted my level that was open. Oops. All right, anyway, we're going to put her there. We're going to select the particle source and delete it. We're going to delete this guy. We're going to delete all these except for that one. We're going to delete this. And okay, so she's walking around. That's great. That's wonderful. Let's put this way over here so we don't like run on it. And now I'm going to put wardrobe instantiate. And we're going to put it there. We're not getting a cowabunga though, which makes me sad. Let's make sure fences still work, right? Okay, that still works. So she's running through there, but that if statement that we put might be, we're only doing it. Yeah, okay. We're only doing that if statement if we're in a beam, actually. Before we close this level, let's clear out some of this stuff that's just like bugging me. It looks like the water's still there, but it's not. It's just something we have to put up with right now. And okay, so we've still got little nubbins down here. I'm going to leave the little water loop because we might do a thing with it. All right, cool. Now, let's go change where that is. See, this is only if we're in the squeeze beam. The alter squeeze beam. That's not right. We could put it there, though. Do you ever need new tools for the game design? What do you mean tools? What are tools? Cowabunga! Cowabunga, cowabunga, cowabunga. Okay, okay. So let's do a little bit more stuff now. Let's have a couple of blocks over here. We're going to make this a little bit like a level. Okay. And I'm thinking that maybe you, I don't know exactly how we're going to use this, but like, I'm thinking maybe you can't go back out unless you have the ability that it gives, right? So it would block you. That's a sort of random decision, but it sounds interesting, and we could decide later if that's how it really should be. But anyway, so you're not going to be able to get to that side unless you go through one of these. And we have, so this one's going to be multi-push, which is warrior. This one's going to be pull. And this one's going to be, let's just say, teleport. Let's do 4. This one's going to be transmute. Let's do 5. Why not? This one's going to be charm. And mapping these to colors, I'm probably going to have to write some annoying code. But there, we can cowabunga through each of these. And you know what? It should be a very small amount of code. Whoa. I don't know what that noise was. This should be a very small amount of code to just make this happen. And then the graphics can come later. Okay. Oh, there's an invisible something, isn't there? Bro. Bro. What was he doing there? All right. Now the thing is, I also can push things through here. And by the rules of the game, that would do stuff to them. But we're not going to worry about that yet. Okay. Achoo! So the x-axis of these is forward. And so if you're moving along the x, we would add the thing. And if you're moving along minus x, we would remove it. Okay. Object to world space. Object to world. Oh, you know what? So we have a vector along the x-axis, and I'm going to say forward equals rotate, actually, this by wardrobe.orientation. All right. Now, if dot product info.delta forward is greater than some epsilon, let's Let's give that a different name. I like to do that. So we're going to say if, okay, if we know we're dealing with a guy, which guy is a gender neutral term in this game. So if we don't have wardrobe.skill flags, okay. All right. And if you're going out, we remove those flags like that. Okay. So I started inside, but I didn't have. All right. So added pull. So she doesn't have a pulling animation, but she could pull stuff. That's great. She could also push things, which we actually, I'm going to put that on the notes. Do we remove her ability to push? I don't know. Okay. Now she has warrior and thief right now. So she could push multiple things. Okay. Removed pull. Removed multi-push. See, video games are cool. You know? Feature complete, ship it, I know. So this is going to be a little bit hard to play initially because, like, I don't think these respond to color at all. Oh, they sort of do. LOL. Okay, that's not. Let's do these in order. Charm. Okay, actually, we're going to have the color set on this. And then we will just set her cape color, and that way I don't have to like hard code it in the program. Okay, so that's purple nurple. Let's actually set that on all of them. All right, so purple, this was multi-push. That's going to be warrior red. This was pull. So that's going to be green. This is teleport. That's going to be blue. This is transmute. That's going to be like a poopy brown. This is Quentino's less well-known money, poopy brown. Less well-known movie, I mean. We should also... Like, while we're doing this, we should be serious about it. Let's Let's get one more. This one is going to be protection. In fact, we'll do all of them. Immunify. That's such a weird name that I picked a long time ago. So immunify is going to be yellow, and then we'll do take gems. Wait, I just replaced transmute, didn't I? That's not good. This is yellow. Okay. Let's just do it this way. There's the camera. And then we'll do one more, which is can take gems, which is the promised dude, which is gray. Gray. Okay. And then we'll put a gem. I mean, we could do that there. Okay. You know, while we're, let's just frickin'. So she has 3 rows below, 2 rows below. I don't know. Let's just do that. Boom. Sag. Okay. Oh, because we have charm. Yeah, charm kind of doesn't interoperate with some of the other ones. We'll put a monster. One of these dudes. Oops. Yeah, this is cool. We should have done this before. It's pretty fun. I'm already having fun. I'm already having fun. Ship it. Does it detect when you teleport through? Right now, you skip it, and that might be good. although it might be bad. Right now, you go past it. Okay, so now I want to do the part where we decide if you can go through. Oh, we should also set her cape color. Although, that's not that good yet. We'll just say... We'll just set it. I don't know. There's nothing really correct to do here. I don't know. Ta-da! It's almost like we actually did the art for it. Okay, this is already real fun. How come the monsters don't move around? Because they are lazy, like most of the viewers of this stream who do not program enough. Like, why are most of these people watching Twitch instead of programming? It's the same reason. It's the same reason. I mean, ship it. We should make this more nice a little bit. I just feel like I want to do this and that and this and that and that and that. And then there. Okay. So we're going to save this because other people wardrobes. Okay. Now, can go. We have is fence between. That's for goblin. We're not going to think about that for now. Okay. If is wardrobe between. Okay. Okay, so okay. Okay. eh, eh, eh. I want to set up a sneaky tunnel for people to get out. Just so I can do extras. Now maybe those should be affectable, but yeah, we'll see. I mean, guys, I'm done. I don't know what to tell you. It took less than an hour. I don't know what to say. Yeah, ship it. I think we ship it. I think we ship it to the people and let them do shit. I will send an email to the people explaining. Will this double the puzzle count? I hope not. No. No, no, no. All right. I will... So first, let's commit this. You know what? We'll make a release build and run a Benny test for a short amount. Just to make sure I wasn't really stupid. If you pull a block, can you go through the gate again? Yeah, because you would be pushing the block out of the way. However, you could imagine some other situation. Well, you can always push if there's nothing behind it. Like, to pull it into that square with you going out the gate in the same move, you have to be pulling it from the direction in front of the gate, right? Which means that square has to be empty. I mean, maybe something fell into that square later or whatever, and then yes, that would block you. For sure. What happens if you undo the move that gives you one of the abilities? Well, you'll lose the ability, which we can test just now, but... I'll show you. I will show you. So here we'll get pull. I'm pulling. I'm undoing out the door. Now I can't pull. See, as you will see, if I walk around the cheat zone, I'm not pulling anymore, and I can't multi-push, and I can't do nothing. Now I can. Oh yeah, oh yeah. Can you teleport through the gate? Yes, you can. And that is a way to sort of maybe break things. And it's going to be under discussion whether that's desirable or not. But I didn't think it would be good to preemptively prevent that. Although we could have teleports stop at the gate or whatever. Now check this out. Because I have transmute and protection, I can go doink. It might be a bit confusing that you don't get the message the ability is removed if you undo, then you're bad at the game. If you think that you would keep the ability, you're bad at the game. Also, those messages are not, that's not how we're going to give people that information in the end. It's going to be on the character. Okay. Now, okay, well, I don't know what else to say here. Okay, we're basically, like I said, we're basically done. So let's reset. Oh yeah, I was going to Benny test here. And I will dictate to you the email that I type. Oh, cool. One of our testers sent us a new video. I am typing an email. Oops. I'm going to say added wardrobes to the game. There's a new level called wardrobes where you can try this out. It's in drafts. So you have to be in the editor to load it. Then just Control F11 to play. Pasting the screenshot, and I'm going to say, there are a number of decisions to make about this that rather than preemptively make, I just left as permissive as possible and clamp down on it. And we can clamp down on it as necessary. The way it works right now, you can walk through these in the forward direction, which is up in this screenshot. But you can only walk back through it if you have the particular ability that gate grants you. So we could have multiple gates going into the same room, and you can only get out through the one you went in. unless there is another way out. Currently, you can teleport past one of these and skip it and keep the teleport skill. Maybe that is bad, scary, dangerous. Or maybe we are confident we can design so that that's not an issue. If we want, we can block teleports at the wardrobe or something else. Graphically, I'm skipping back a paragraph to explain. Graphically, I am imagining the clothes would be hanging in that doorway, hanging in the wardrobe, blocking the way visually if you didn't put them on. Going back to the first paragraph, just press Control F11 to play. It is super fun just screwing around on this level. It has that we should have done this a long time ago feeling, which is always nice. It was very easy to implement as well. Caveats below. Okay, currently you can teleport past. I do not allow other magic affectable stuff like crystals through the wardrobe. If we decide we want that, we could make it happen, and that could be kind of interesting and or crazy for the basement. Do not currently, but this should work with overworld clones, so you could have a clone set up where each character gets a different skill. I do not currently remove the Queen's push ability when you go through one of these. So if you go through the thief wardrobe, you can pull and push. And maybe that is bad for what we want to do. Or maybe it's more interesting since we can make puzzles that we could not otherwise make, and in general the overworld would feel a little different rather than just a thief puzzle that is arbitrarily on the overworld. Okay. I do currently let you walk through multiple gates at once if you want. That's why there is a cheat side passage on this level to get out without taking off that outfit. The colors, the cape color doesn't show correctly if you have two abilities and remove one, but we can think about that later on if we decide it should work this way. It is pretty fun having multiple abilities, and there can be weird stuff having to do with this. For example, if you have teleport plus gem pickup, you can only pick up a gem when, if pushed onto it, if pushed onto it by a rover or something, or falling onto it. Because the Bard code is still kind of different from other code, it doesn't interoperate with a lot of these other abilities. So I would not necessarily recommend having Bard plus other stuff. That said, maybe this could be fixed long term if we really want to do it, or maybe it does not matter. The promised guy's inability to turn is tied to his skill flag right now, which means that when the queen gets gem pickup, she cannot turn when blocked. Maybe that's bad. Maybe it's good. Long term, I am still wondering whether this is a game feel mistake to begin with, and it should really be just that character plus artifact that causes turning blockage. We never considered this possibility, maybe because it seems a little specific / niche, but I think fictionally it could be explained in cutscenes if we want to go that way. Okay, maybe that's everything. Oh, let's talk about, okay, so visually, obviously we want in the near term a mesh that looks like you can walk through it. Then I could just draw a square representing the outfit if it's on the wardrobe, and not draw that square. A square that is kind of arch-like. Outfit if it's on the wardrobe, and not draw that square if it's clear. We would want a mesh. Okay, that seems like everything to say. And the Benny test is going fine. Sure is taking a while, but it's fine. So I'm gonna send the email. And I'm gonna commit this. Added wardrobe to the game. GG. That's another thing that was so easy today. Boy, game programming is so easy, guys. Let's not commit these, though. That's all I wanted to do on the stream. That's the whole stream. Like what? The game's done. Ship it. Time for a nap. I actually had a nap before the stream. How big is the team? We're like 15 people right now or something. Well, not all those 15 people are working directly on the game. So less than 15 people. But it's a freaking lot of people, dude. Time for some gaming. Maybe. I just don't know if I can tolerate Call of Duty anymore. I just can't. I would rather... It's kind of like Tarkov now, where I would rather watch someone stream Call of Duty than actually play it. Like I was watching Grims this morning. Our old pal Grims, who we ran into in Blackout a couple times. Or no, we ran into Grims one. No, we never ran into... I don't know. We ran into Huskers a couple times. Anyway. No, we ran into Grims once, didn't we? Anyway. I was watching him and he was getting aimbotted and like dying in like 113th place and whatever. So, yeah. It's even for people who are very, very good at these games. It's rough sometimes. Time for fixing other things like a charm thing. You know, we could think about the charm thing now. Before we do that, I'm going to make a note for the team about what I did, and I'm going to get some water because if I don't get water, I'm going to drink another very caffeinated Golden Monkey, and we don't need that. How come people with different Twitch names keep typing the same thing? Multiple people have typed, "What about some beans and nothingness? It's on your desktop." I'm about to ban you all. What do you think you're doing? If you bother me about that kind of thing across multiple streaming sessions, which is what's been happening, you're just going to make me annoyed. Like, I'm not going to suddenly say, that's a great idea. Is it possible to read and modify code passed into a compile time function? Yes. Yes. What is the representation that the metaprogram sees? Go watch some streams, dude. It's in the streams. I don't want to explain right now because it's a long explanation. But it's basically a syntax tree. Yeah, it's a strongly typed syntax tree with type information. Okay. You've heard me say that stuff is out of date. Well, here's what I would say. is that in terms of this particular topic, some specifics are out of date. But if you watch the ones about, so, and in fact, in those streams, I never had this specific capability that you're talking about, but we do now, and it's the same representation. So if you watch the one, if you care, I mean, maybe this is enough of an answer for you already, but if you care about details, you can watch the ones where we use the meta program to do, compile time code modification. And then the answer is it's that same representation, just you see it and modify it from a different place, from, within your function or whatever. And we do that because why it would be super confusing and not that useful to have multiple representations, and it would make the compiler more complicated. Okay, added an initial implementation of wardrobe entities, which is cool. Okay. Let's finally look at the charm thing. What advice would I tell a random person I don't know who barely knows how to program? I would say try to learn programming. Like what? I don't know. What's the 3D lib used in the engine? What? What do you mean by 3D lib? Do you mean the API? I mean, we target multiple APIs because we're shipping on a number of platforms. Wondering if it's possible to do something like implement a for each loop that automatically spits out an unrolled SIMD version that manages masks automatically. I mean, I have not tried that specific thing. I think it a little bit depends on the specifics of what you're trying to do. Like, is it you're calling some macro that's like, do this thing n times? The thing is, because, I mean, is n static or dynamic? I'm imagining it's dynamic. Because if it's static, that's hella code bloat, right? So you would have some macro that's like, I want loops that do this 32 at a time, but n is a runtime number or something. You could do that. I mean, what I suspect is that there might be some things that are suboptimal that then, that kind of use case, because not that many people are doing that yet, we haven't smoothed out all the little tiny issues that people run into. And so it's instructive to see people do stuff like that. And then when we run into problems, we solve them. Oh, the Casey project video? Yeah, I don't think the Casey project video ultimately did anything useful, though. And I think that was before we added a few features that are really useful in macros. How do you know if the operations within the for each don't touch values from within the array? I don't understand the question. Don't understand the question. Okay. Well, oh, right. Yeah, if it's an aliasing question, then yeah, that's up to the programmer. And that's not necessarily, in systems languages, especially with SIMD and whatever, that is not really a new thing, right? It's like yeah, you're expected to use it correctly, I think, is the answer. Now, that said, anytime we can add stuff to help notify people when they don't use it correctly, right? That's very helpful, right? Error messages are helpful. The thing is, sometimes it's really hard to know. It's really hard for a system to know, right? And would be dynamic with a 4-wide unrolled version of the user's code. Yeah. That might even be what I was trying to do in the KC project video. But like I said, it was before it was like, that was like a year or 2 years ago. I don't even know. And it motivated addition of some features. Anyway. Yeah, so we were going to do this charm setup. That's in enact move, right? So this charm setup is it's stored on the transaction because I didn't want to make a table for it that maps thing to thing. And that's bad because it complicates the core system. And, the whole deal is we had a bug that was causing problems that involved this charm setup not getting copied from a transaction to a copy of the transaction, right? And I was like, what the hell is this? And it turns out it's just here so that this piece of code can be lazy. And it's my fault. I did it that way. But we're going to clean that up. And so right now we say this charm setup is on the single move. And instead of that, we'll build somehow a cross reference. The thing is, we can't use the pointer to the single move as like a hash table key because that moves. And in fact, I wonder if we can remove stuff from the array and all these things. And so we maybe have to think a little bit about what exactly we're going to review the code for a minute, and then we'll decide what to do, basically. Yeah. I think I think my answer ultimately to the SIMD thing is you definitely should be able to do that. And to the extent that you cannot, that illustrates things that we should fix, right? Anyway, okay. So charm setup. So I think that's the first message of or usage of charm setup, yes. And then so charm setup has an array of move infos that's dynamically sized. Because okay, the whole deal is when dudes are on other dudes, so to speak, they could move multiple squares due to charmed movement. Right. So we don't actually use the charm setup very much. And then if I search the rest of the program, yeah, it's in move transaction, but really just the declaration and the clearing it, right? And then this is also like clearing it. Oh, wait. Oh, no, this enact move, that's the code that we're looking at right now. So, yeah. Let's just start this charm setup. We're going to move this. See, I have this comment. It should not be on the move transaction at all. It's literally that. Okay, so in move transaction, we're just forcing ourselves. Oh, no. Okay. I guess we, yeah, I guess we serialize this. So single move is version 8 now. This is going to be 5 to 7. This is going to be we're going to keep this around. Sometime when we get rid of save games, deprecated. Sometime when we feel fine with toasting old save games, we'll delete these. That's, you know, that's what we do. It's how we do it. So charm setup. Charm setup. When did we clear this out? In close, right? And then in undo, charm setup. Wow, did I write that? Did I write this during the stream where I said remind us to clean this up? No, I think it was later, but it took 12 days, dude. How lazy am I? All right. So now the only use of this variable is in enact move. Okay. Now the problem is I'm confused because we supposedly cleared this out in close. This code isn't even going to frickin' do anything. Oh. Right, and I think this just broke. I don't actually know. You know, I should have done a Benny test and gotten a list of what, yeah. We know what levels to try, though, for this. So we're going to no check in this for now. Because that see, in move transaction, yeah, that's not okay. All right, so we might not even need that code. Yeah, this is weird because when I first programmed this, I seemed to think it should live for the duration of the transaction. And now it's probably like, oh, we don't want to serialize that. But the way that I handle this is kind of bad. This is kind of bad because if I actually do need to preserve it longer, I should write this code that I'm about to write differently. But you know what? Screw it. If I need to do that, I'll change it. Charm setup. Cater is temp, array resize. Charm setups found.count. Okay. No, that's not right. So we actually add moves down here. Okay. Single move. I'm going to assume they don't get rearranged. All right. So oops. Let's just let the compiler tell us what line is broken. Okay. Add charmed MDs. Okay, so here's what we're going to do. Okay. So cinfo is charm setups sub it index assert cinfo.single move index is equal to it index. Okay. So we're going to do this. We're going to put new move infos. Instead of, and then if new move infos fake global move infos. Oh, that's new. Okay. It's fine. Okay, I don't feel like I declared this in the right place. Okay, so new move infos is going to be out here. That's the new mofos, right? And then E single is okay, assert E single index is greater than or equal to 0. And C setup is charm setups E what? Single index? Why do I not see? Oh yeah, it's right up there. C setup dot move infos equals new move infos. I'm going to move this assert down here. Dude, I have no idea what this code is doing. 1994, that was a good year. Kinda. God only knows what's going to happen now. Okay, so this is fine. Now this is the barred code, so we're just going to... Oh! We already crashed, so that's fun. Let's run in the debugger. Okay, so boom. Add charmed entities to transaction. E single index is greater than or equal to 0. I did not catch it. So there's some other okay. Easy clap. Easy clap. Eric Clapton. Okay, well, I messed it up here. Add charmed entities to transaction. E single index is 0. Charmed setups. There ain't none. You know what? This is not the right way to do it. Instead of E single index, we have new charm setup. We're just going to add this. Okay. E single index equals, instead of that, right, we're going to do this. And we're going to do this. And do it here. Okay, we are not tracking an index. Neuralink event is right now. Oh yeah, let's watch the Neuralink event. Let's see if this crashes. Let's put the... Hey, look, I can charm. Okay, we'll try the real stuff later. You guys ready to watch the Neuralink event? Sorry, I'm trying to find the link. I can't find the link, dude. Aha, here we go. All right. You ready for the Neuralink event? No.
You tweeted that if the price of Bitcoin doesn't go to $1 million by 2020,
I will eat my member, yes.
you will eat your own.
Eat my... No, I may choose the mode. If I choose to get a Bangkok prostitute and ask her, would you please eat my over the next 5 years, that's fine.
That's different than eating your own.
Is it now?
Because if a Bangkok prostitute ate your, you wouldn't be eating your own.
Do I not have the privilege of subordinating my task to a subordinate?
To someone who doesn't know a lot about Bitcoin,
Yes.
it sounds like you, John McAfee, want to eat your own.
Eating my is not something that is difficult. For me eating it, I have no interest in doing that.
So it isn't that you, John McAfee, want to eat your own. It's that you believe in the power of Bitcoin, so much so that you'll put your on the table, chop it up, put it in your mouth, swallow. If Bitcoin does not.
If it doesn't reach at least $1 million by the end of 2020.
What if, God forbid, you get prostate cancer, have to remove your anyway?
Well, I won't be able to eat it, will I?
Well, you can have the surgeon put it aside and then you can eat it, but either
I
way.
don't think people would expect me to eat a 2-year-old dead I'm sorry.
If John McAfee is to eat a it's going to be the freshest
And
right
eat it
away.
raw like I eat sushi.
Farm to table to mouth.
On the table.
Wow, Neuralink is always coming up with amazing things. I don't know how the Neuralink press conferences are always so good. You know, you know, all right. Starting soon, it says. Starting soon. Oh, it just changed. The picture is changing. I have to get my important Twitch chat up though. Oh, it changes back and forth. Okay, never mind. That's a tactic to make you think something's happening. So basically what's going on is Elon's late again. And they can't start till he gets there. He's in San Francisco. The Twitter office is, okay. I think it's a 10-minute walk from the Neuralink office, right? So here we go. The Neuralink office is at, what's it called? I almost rented part of what became the Neuralink office later. Shit, what's the building called? Pioneer, something factory. Yes, here, this is where Neuralink is approximately. All right. This is like where Twitter is. So let's put a pin here. Save. Starred place. All right. Twitter HQ. Okay, it's here. We'll get directions from Twitter HQ to Pioneer Trunk Factory. 6-minute drive. 23-minute walk, which is longer than I thought. All right. That's why he's late. He just started walking. He stopped at the DNA Lounge to do some goth industrial dancing. By the way, our office, where we worked on this game for a while, was the old office of another game company who I don't know if I should dox, but they make games such as Transistor and Bastion and Pyre, and we took over their office, and it was where is it? It's so weird looking at this. It's like here. Where's the Starbucks? We're on the same there. Okay, we're right there. 505. That's where we used to be. Is that the big concrete one? The big concrete what? They must be renting someplace only Hades could pay for now. Well, they bought, when we took over their rent, it was because they were annoyed that the rent was so high. And they bought a building over in Hayes Valley, which is like around here somewhere. I don't know if they still own that building or what. They don't seem to have expanded. That's the interesting thing is, you know, Hades has been very successful, which is great. Enough that they could expand a lot if they wanted to. But I have not heard of them doing that. I think they're staying a modestly sized company for now, which is great. They bought it. Yeah, I believe they bought the building because long term it was just going to be cheaper than renting. Right? So, yeah. I don't super know the details. I was just talking to one of the people involved way back. I mean, this was, I don't even know what year this was. 2018, 2017. Something like that. Their office got totally ransacked in June 2020 protests. Really? Oh, that sucks. That is lame. That is lame. Right? Let me see. If we search for Neuralink, will it say Neuralink chiropractic? So Google Maps doesn't know where Neuralink is, probably because loonies will attack them, but it's there, by the way. Anyway, my mic is really low. What? No, it's not. Dude, I've been streaming all day. What are you talking about? 3180 18th Street, yeah. Well, I don't know if that's 3180. Let's see. Yep, I told you. I told you. Do the people in general think my microphone is really low? Oh, you know what? I bet we rebooted Windows and it turned down the levels again.
New developments to share with you that I think are incredibly exciting, as well as tell you about the future of what we're planning to do here. It's and now this is meant to be a technical podcast, sort of like a. I'm going to provide an overall summary, and then we're going to have a number of members of the Neuralink team come in and give a deep technical overview of the various areas. So
this is going to be long and kind of boring.
With the overall summary. Now, some of the things I'm going to say are things well, if you've been following Neuralink, you've already heard before. But for a lot of people out there, they've no idea what Neuralink does, and so I'll be a little bit repetitive of things you may already know, but that others do not. So, the overarching goal of Neuralink is to create ultimately a whole brain interface. So, a generalized input-output device that, in the long term, literally could interface with every aspect of your brain, and in the short term, can interface with any given section of your brain and solve a tremendous number of things that cause debilitating issues for people. So, you know, so our long term is I'll talk a little bit about our long term goal. It's going to sound a little esoteric, but it was actually the sort of my prime motivation, which was, you know, kind of what do we do about AI? Like, what do we do about artificial general intelligence? If we have digital superintelligence that's, you know, just much smarter than any human, how do we mitigate that risk at a species level? How do we mitigate that risk? And then even in a benign scenario where the AI is very, very benevolent, then how do we even go along for the ride? How do we participate?
I'm
And
free. Finally.
The thing that the biggest limitation in going along for the ride and in aligning AI, I think, is
What?
the bandwidth, the how quickly you can interact with the computer. So we are all already cyborgs in a way, in that your phone and your computer are extensions.
Oh, it's not even
And I'm sure you found, like, if you
on the overworld.
leave your phone behind,
Bro.
you might end up tapping your pockets, and it's like having missing limb syndrome. Like, where, you know, the phone is leaving your phone behind is kind of like a missing limb at this point. You're so used to interfacing with it. You're so used to being a de facto cyborg.
Okay.
But so what's the limitation on a phone or a laptop? The limitation is the rate at which you can receive and send information, especially the speed with which you can send information. So if you're interacting with a phone, it's limited by the speed at which you can move your thumbs, or the speed at which you can talk into your phone. This is an extremely low data rate. You know, maybe it's like 10, optimistically 100 bits per second, but a computer can communicate at you know, gigabits, terabits per second. So this is the fundamental limitation that I think we need to address to mitigate the long-term risk of artificial intelligence, and also just go along for the ride. And
I'm free.
so, but like I said,
hold on.
that's an esoteric explanation that I think will appeal to a niche audience, some of whom may be here. And that's a very difficult problem. So even if we do not succeed with that problem, I think we are confident at this point that we will succeed at many. It's solving many brain injury issues, spine injury issues
hell?
along the way. So, yeah. So, anyways, so actually we have Justin Roiland in the audience. This is hi, Justin. So it's a little Rick and Morty reference here. This great Rick and Morty episode about intelligence enhancement of your dog, and what's the worst that can happen? So anyway, Rick and Morty, I recommend it. So so you want to be able to read the signals from the brain. You want to be able to write the signals.
Bro,
You want to
you're
be
taking
able to
out my
ultimately do
levels.
that for the entire brain, and then also extend that to communicating to the rest of your nervous system if there's you have a sort of a severed spinal cord.
Okay, that's what I wanted to know, really.
So now this is this video is now 18 months old. So this is Pager, who is playing monkey mind pong. So this is Pager has a Neuralink implant in this video, and the thing that's interesting is that you can't even see the neural implant. So we've miniaturized the neural implant to the point where it matches the thickness of the skull that is removed. So it's essentially it's sort of like having an Apple Watch or a Fitbit, replacing a piece of skull with like a smartwatch, for lack of a better analogy. So you can see, you can really can't. He looks he's normal, and I think that's pretty important. If you have a Neuralink device, like I could have a Neuralink device implanted right now, and you wouldn't. You wouldn't even know. I mean, hypothetically, maybe one of these demos, in fact, one of these demos I will. Yeah. So yeah. Anyway, so here's first of all, it's kind of wild. Hey, monkeys can play Pong. They can actually play Pong if you give them a joystick. So Pedro first learned to play Pong with a joystick. So I'm like, that was novel. It's like I didn't know monkeys could play Pong, but they can. And then so we first trained Pedro to play Pong with a joystick. Then we took the joystick away and have the Neuralink. And now he's playing It's a telepathic video games, essentially. So what we've been doing since then is we've been on the very difficult journey from prototype to product. And I've often said that prototypes are easy, production is hard. It's really, I'd say, 100 to 1,000 times harder to go from a prototype to a device that is safe, reliable, works under a wide range of circumstances, is affordable, and done at scale. It's insanely difficult. I mean, there's an old saying that that it's 1% inspiration, 99% perspiration, but I think it might be 99.9% perspiration. The best example I could give of an idea being easy, the execution being hard, is going to the moon. It's the idea of going to the moon, easy. Going to the moon, very hard. So, we've been working hard to be ready for our first human, and obviously we want to be extremely careful and certain that it will work well before putting a device in a human. But we've submitted, I think, most of our paperwork to the FDA, and we think probably in about 6 months we should be able to have our first Neuralink in a human.
I don't know. Somewhere we're adding extra moves.
But
And I
as
don't
I said,
know where.
we do everything we possibly can to test the devices before, not even going into a human, before even going into an animal. So we do benchtop testing, we do accelerated life testing. We have a fake brain simulator that has the texture, and it's like emulating a brain, but it's sort of rubber. And so before we would even think of putting a
I
device
bet it's here.
in an
Oh,
animal,
no, 'cause there's no gate.
we do everything we possibly can with rigorous benchtop testing. So we're not cavalier in putting devices into animals. We're extremely careful, and
Oh, duh.
we always want the device, whenever we do the implant, if it's in a sheep or a pig or monkey, to be confirmatory, not exploratory, so that we've done everything we possibly can with benchtop testing, and only then would we consider putting a device in an animal. Yeah, we'll actually show you a demo later today in a few hours, really, of implanting in a brain proxy. And if anyone in the audience wants to volunteer, we have the robot right there. So let's see, and since the Pager demo, we've expanded to work with a troop of 6 monkeys. We've actually upgraded Pager. They do varied tasks, and we do everything possible to ensure that things are stable and replicable, and that the device lasts for a long time without degradation. So, and what you're seeing there is, it looks like the matrix, but that's actually, that's a real output of neural signals. So that's not a simulation or just a screensaver or something. Those are actual neurons firing. That is what one of the readouts looks like. And here you can see Sake, it's one of our other monkeys, typing on a keyboard. Now this is telepathic typing. So to be clear, this is he's not actually using a keyboard. He's moving the cursor with his mind to the highlighted key. Now technically, we can't actually spell, and so I don't want to oversell this thing, because that's the next version. But what's really cool here is Sake the monkey is moving the mouse cursor using just his mind, moving the cursor around to the highlighted key, and then spelling out what we want to spell. But and then so this is something that could be used for somebody who's say quadriplegic or tetraplegic human, even before we make the spinal cord stuff work, is being able to control a mouse cursor, control a phone, and we're confident that someone who has basically no other interface to the outside world would be able to control their phone better than someone who has working hands. So. And I mentioned upgradability. Upgradability is very important because our first production device will be much like an iPhone 1, and I'm pretty sure you would not want an iPhone 1 stuck in your head if the iPhone 14 is available. So it's going to be being able to demonstrate full reversibility and upgradability, so you can remove a device and replace it with the latest version, or if it stopped working for any requirement for the device at Neuralink. And I should say both Sake and Paige were upgraded to our latest and greatest implants. That's been really a year. Paige's had the first implant and then the upgraded implant. So this is a very good sign that it lasts for a long time with no observed ill effects. I think it's also important to show that Sake actually likes doing the demo, and is not like strapped to the chair or anything. So it's yeah. So the monkeys actually enjoy doing the demos because they get the banana smoothie, and it's kind of a fun game. So I guess the point I'm trying to make is like we care a great deal about animal welfare, and I'm pretty sure like our monkeys are pretty happy, you know. So as you can see, a quick decision maker on the fruit front. So for our the first two applications we're going to aim for in humans are restoring vision, and I think this is like notable in that even if someone has never had vision ever, like they were born blind, we believe we can still restore vision. Because the visual part of the cortex is still there. Yeah, even if they've never seen before, we're confident that they could see. And then the other application being in the motor cortex, where we would initially enable someone who has no ability, almost no ability to operate their muscles, you know, sort of like sort of Stephen Hawking type situation and enable them to operate their phone faster than someone who has working hands. Then even better than that would be to bridge the connection. Take the audio signal from the motor cortex, and let's say somebody's got a broken neck, then bridging those signals to neural link devices located in the spinal cord. So we're confident there are no physical limitations to enabling full body functionality. So even as miraculous as it may sound, we're confident that it is possible to restore full body functionality to someone who has a severed spinal cord. Yeah. All right. And then I want to emphasize again that the primary purpose of this update is recruiting. A lot of times people think that they couldn't really work at Neuralink because they don't know anything about biology or how brains work. And the thing that we really want to emphasize here is that you don't need to, because when you break down the skills that are needed to make Neuralink work, it's actually many of the same skills that are required to make a smartwatch or modern phone work. So it's sort of, software, batteries, radios, inductive charging, and as well as things that are specific to us, like animal care and clinical and regulatory matters. Obviously, machine learning, that phrase is used a lot. But we also need to interpret the signals from the brain, which is a biological neural net, and the best thing to interpret a biological neural net is a digital neural net. So this is, if there's one message I want to convey, it is that if you have expertise in creating advanced devices like watches and phones, computers, then your capabilities would be of great use in solving these important problems. That's more than anything the message I want to convey. Let's see. Yeah. So with that, I guess DJ. So DJ's was on the founding team of Neuralink and has made immense contributions to the company, as have many of the others who will present. But I want just to thank DJ for his immense contribution to Neuralink and great. All right. Cool. Thank you.
Thanks, Elon. When I moved from South Korea at age 13 and needed to learn a new language to communicate, I wondered whether there are better and more effective means of communicating my thoughts to the outside world. And watching Neo learn Kung Fu in The Matrix, I remember thinking, wow, I want to work on that, work on making that possible. And today, I believe that this is a tractable engineering challenge. Since everything about your intentions, your thoughts, and your experiences are all in your brain, encoded as firing statistics of action potentials, if you're able to put electrodes in the right places with the right sensing and stimulation capabilities, this and many other applications that Elon talked about are possible, and we can help a lot of people. I'm incredibly excited to be working on this ambitious yet important mission to make that future a reality here at Neuralink. And I'm also incredibly honored to be working with some of the brilliant colleagues, scientists and engineers across many engineering disciplines, to work on this intersection of biology and technology. You'll hear from several of them today to learn about the breadth of technical challenges we face and our progress in the last year.
Not very many viewers compared to Mr.
And
Beast.
I think you'll find that for most of these challenges, as Elon mentioned, you don't need a prior understanding of how the brain works, and that a lot of what we do is applying engineering first principles to biology. So how do you create a high bandwidth generalized interface to the brain? From day one, we focused on a set of foundational technologies that are safe, scalable, and capable of accessing all areas of the brain.
It feels to me like this whole
These three
presentation
axes,
today is going to be
safety,
boring and
scalability, and access to
uneventful.
brain regions, really form the basis for how we engineer products here at Neuralink. Safety, because we want to make our devices as well as the installation as safe as possible so that we can drive the adoption of this technology. And scalability, because as we make our devices safer and more useful, more people will want it. And with scale, we also want to make it more affordable. And access to brain regions so that we can expand the functionalities of our technologies. So our first steps along these dimensions for our device is what we call the N1 implant. It's a size of about a quarter, and it has over 1,000 channels that are capable of recording and stimulating. It's microfabricated on a flexible thin film arrays that we call threads. It's fully implantable and wireless, so no wires, and after the surgery, the implant is under the skin and it is invisible. It also has a battery that you can charge wirelessly, and you can use it at home. So similarly, for implanting our device safely into the brain, we built a surgical robot that we call the R1 robot. It's capable of maneuvering these tiny threads that are only on the order of a few red blood cells wide, and inserting them reliably into a moving brain while avoiding vasculature. It's quite good at doing this reliably. And in fact, because we've never shown an end-to-end insertion of a robot in action, we're going to do a live demo of the robot doing surgery in our brain proxy. So who wants to see some insertions? So here it is. That's our R1 robot with our patient Alpha, who is lying comfortably on the patient's
I mean,
bed.
so Elon said this in the beginning. Basically, they're on the road to productizing it, and that is a long and difficult road, and that's all true. Like, that just is what it is. So their earlier presentations from previous years were all the like, this is what we're going to do, and that's really exciting. And now they're actually trying to do it, and it's going to be kind of boring for a while because they're going to be still partially along the roadmap of what they already said, right? So they're not going to say much that's new.
Insertions. So this is another view real quick. On the left is the view of the insertion area, and on the right, what the robot's going to do is it's going to peel the array, the threads one by one from its silicon backing and insert it into the targets that we predetermined in the targeting view. So
I really don't want to do this to my brain. I'll tell you that.
there you go.
Ah,
That's the first
no.
insertion.
Oh, God. They should not have showed this video, by the way. This is
So
going to
we're
make
going to see
people
a
not
couple more
want it.
The whole process of inserting about 64 threads in our first product is going to be around 15 minutes for this robot. So yeah, there's a second one that went in, and we're going to do it.
Way to make people not fucking want it, dude.
There you go. And then that's going to go in the background, and we'll come back to it in the later.
Oh, gross. This is going to give me nightmares, guys. Do not show that.
And as Elon mentioned, we've been working very hard to go from prototype to building product. As part of this, one of the things that we did is to move our device manufacturing to a dedicated facility.
Oh, that was such a huge mistake.
For scale-up manufacturing. And what's important to highlight, and is evident in this clip, is that it's very typical for us to have our engineers who design also work on the physical manufacturing line to build and debug. And this has been
So did he just say
extremely-
their new facility is in Austin? So Neuralink is in the process of moving to Texas as well, probably. It's just all the old employees still live in San Francisco and don't want to move.
So we now have a dedicated, our own OR, in fact, a double OR in Austin. And this is just a stepping stone before we eventually build our own Neuralink clinic. So with this product, N1 and R1, our initial goal is to help people with paralysis from
He might have
complete spinal
said
cord
Boston,
injury
but I think he
regain
said
their
Austin.
digital freedom by enabling them to use their devices as good as, if not better, than they could before the injury. And as Elon mentioned, over the last year, this has been the central focus of the company. And we've been working very closely with the FDA to get approval and to launch our first in-human clinical trial in the US, hopefully in the next 6 months. So hopefully this gives you a good overview of our product. For the next hour, we're going to go through a deep technical dives on these topics to tell you about our technical challenges, share some of our progress, and
Yeah, it's going to be
preview
boring.
what's coming next. So with that, over to Nir from my team, who's going to talk to you about neural decoding.
Thank you, DJ. And hey, everyone. My name is Nir Evenchen, and I'm the head of Brain Interfaces Applications. Our goal is to enable someone with paralysis control a computer, as well as me, or even better. We'd like to provide fast and accurate control with all the functionality of computers that works anytime, anywhere. So I'm very excited to show you how we're using the N1 device with our software and algorithms to achieve this. Last year, we shared with you a video of Pedro the monkey controlling computer cursor with his brain. So how do we do that? Just a brief reminder. First, we record his neural activity from the motor cortex using the N1 device. We can record from over thousands of channels while he's playing with the joystick. Then we can train a neural net that predicts the cursor velocity from the patterns of his neural activity. With this decoder, we can then control a cursor just by thinking about it, without even moving the joystick. He can play with this decoder a variety of games, also a grid task, where he's moving the white dot towards the yellow target. Every time he gets one, he receives a drop of his favorite smoothie, and he chooses to play this game every day. Here you can see his performance from early 2021, around the time we released the previous demo. It's quite accurate, but it's a bit slower than what we would like. And cursor control is the foundation for interacting with most computer applications. So since then, we've been working to improve cursor speed and accuracy. As you can see, it's much, much faster, almost twice as fast.
Dude, they've got the fucking thing with the employees
It's still
in the crowd
a bit
cheering.
slower
Don't
than
ever
I'd like
do
to
that.
So we are working on creative ways to improve that.
Don't ever do that.
Now, speed is not enough. You want the full set of functionality.
It's like an
And for
Ubisoft
decades,
conference or
most
whatever.
software was built for mouse and keyboard control, and it doesn't make sense to reinvent this entire ecosystem for brain control, at least for now. So we are working and we are designing mouse and keyboard interfaces for the brain. The way we do that is by training Pedro and his friends on a variety of computer tasks, and then designing algorithms to predict their behavior. Here you can see a few examples of tasks in different phases of monkey training. For example, left and right click, click and drag, cursor typing, swipe typing, handwriting, and even hand gestures. Now, interacting with computer is bidirectional, and feedback is very important. I like when I click on a button and I can physically feel the button being pressed. When a potential N1 user will attempt to click, they won't be able to feel it. An example of how we are addressing that is by providing a real-time visual feedback that represents the strength of the neural click by changing the color of the cursor. Just by typing on a physical keyboard is much faster and easier than typing on an iPad keyboard. This will make the brain control much faster and easier to use. Typing, one of the most important functionalities. So you already seen this message, and I want to show you the behind the scene of how this message was created. And here you can see again Saki using the virtual keyboard, typing this message. This virtual keyboard is similar to the one I use on my phone. And with the speed and accuracy that we achieved so far, typing on a virtual keyboard is already fast and easy. However, I never use a virtual keyboard when I type on my keyboard, on my computer, because it covers my screen, and it's also much slower than what I can do with my 10 fingers. We can do better. For example, a group from Stanford asked a person to imagine handwriting letters. Then they decoded the letters from his brain activity. Using this approach, they were able to speed up the typing rates. We started this project with our monkeys, but of course they don't know how to write. So to mimic writing, we trained Ranger, one of our favorite monkeys, to trace digits on an iPad. Here you can see him tracing the digit 5 and the digit 2. Then we recorded his neural activity with the N1 device. But now, instead of decoding the cursor velocity, we decode in real time the digit that he's tracing on screen. We had two main takeaways from this project. One, that monkeys are awesome and can learn very, very complex tasks. The second one, that although it can increase the typing rate, it requires hundreds of examples and samples of each of the digits and the characters we wanted to classify. This will not scale. The way we are solving that is by indirection. Instead of decoding directly the digits, we first decode the hand trajectory of on the screen. And then, when we decoded the hand trajectory, we can use any off-the-shelf handwriting classifier to predict the digit and the characters. For example, classifiers that are trained on an MNIST dataset. Why it's so important? It's important because now we can potentially decode any character in any language with only one neural decoder for hand trajectory. It means that you can write in English, Hebrew, Mandarin, or even monkey language, and we can understand you wanted a banana. So there are many challenges ahead of us to improve functionality and speed. And I want to hand it off to Bliss to talk about the third part, how we are making our brain interfaces work anytime, anywhere.
Hello, everyone. My name is Bliss, and I'm a software engineer here at Neuralink. When I use my computer, my mouse and keyboard work how I intend them to, at least like 99.9999% of the time. My goal is to enable a user with paralysis to control their computer as reliably as I can. Here's what we want that experience to feel like. In this video, you can see Saki walking over to his MacBook and choosing to work on his typing task. The entire decoding system works out of the box, and it feels totally plug and play. The first step to achieving this kind of high reliability is to test extensively offline. A typical flow for using the N1 link is to connect over Bluetooth, stream out neural activity from the brain, and then use that neural activity to train decoders and do real-time inference. We've built a simulation for exactly this sequence, but instead of using a monkey with an implant, we use a simulated brain that injects synthetic neural activity into an implant sitting in a server rack. From the point of view of that implant, it's in a real brain. This simulation runs on every code commit to validate that from the hardware all the way up through to the neural decoders, our entire stack can achieve state-of-the-art performance. However, while this kind of simulation is great for integration testing of software and hardware, it's not yet detailed enough to guarantee high reliability in the real world. In the real world, the underlying signals we're trying to decode actually change day to day. In this plot, you can see the average firing rate detected on a representative channel of Saki's implant. Each bar represents 1 day, and you can see that each day has a different average firing rate than the previous. This presents us with a very interesting problem for how to make our decoders robust day to day. It can actually happen that if you train a neural decoder on 1 day of data and then try to use it on the next, the average firing rates can actually shift enough to cause a bias in the output of the model. Here on the right, you can see that this bias is making it hard for the cursor to move to the upper right corner. You see it struggling here to make it up to the upper right, and then it moves much more effortlessly down to the bottom left. We're trying many approaches to mitigate this problem. Some examples include building models on large data sets of many days of data to try to find patterns of neural activity that are stable across days. Another approach we're trying is to continuously sample statistics of neural activity on the implant and use the latest estimates to pre-process the data before feeding it into the model. This is really an active area of research for the team, and it's a critical problem to solve if we want to enable someone with paralysis to control their computer as well as I can. Another big problem we have is to minimize the time it takes for a spike in the brain to impact the movement of the cursor on the screen. If you have lag or jitter in this control loop, the cursor becomes hard to control, leading to the kinds of overshoots that you can see here on the right. One big improvement we've made towards in this direction is called phase lock. Phase lock aligns the edge of each packet that we send off the implant to the exact moment that the Bluetooth radio is going to wake up. This minimizes the time it takes for a spike in the brain to be incorporated into the prediction of our neural network. Here you can see the latency distribution after phase lock. Not only has the mean been greatly reduced, but the variance has been reduced as well. This makes it easier for the user to predict the behavior of their cursor.
60 milliseconds sometimes? Why
Over
is
the
it
last
that high?
year, we've made tremendous improvements to the stability and reliability of our system. And we've been able to demonstrate consistent high performance across many sessions and many months. However, there's still a long road ahead of us before the system will truly feel plug and play. So if solving the hard problems required to ship this technology is exciting to you, you should consider applying to join the team. Now, I'm going to hand it over to Avinash to talk about how our custom low-power ASIC detects spikes in the brain.
Hi, I'm Avinash, one of the engineers on the ASIC team. We designed the custom neural sensors, which include both analog and digital circuitry, to record and stimulate across 1,024 independent channels. We faced challenges across all 3 major metrics: performance, power, and area. Not only do we have to fit all 1024 channels into a single quarter-sized implant, but we also have to measure spiking activity less than 20 microvolts in amplitude. And today, I'd like to focus on the last challenge I mentioned, power. Power consumption is important to us because we want to give future users a full day of use of their implant without any interruption for charging. Back in 2018, we were sending every sample from every channel off the device for processing, which burned a ton of power. In 2020, we brought spike detection onto the chip. As you may know, neurons transmit information by firing. So simply monitoring for these spikes and only sending these spike events off the implant acts as a very efficient form of compression. And over the past 2 years, we've continued to make optimizations within the ASIC, dropping the total system power consumption down to just 32 milliwatts and doubling battery life. Let's take a look at our on-chip spike detection algorithm, which makes our battery-powered implants possible. We first start by applying a 500 Hz to 5 kHz bandpass filter to remove noise that's out of band. Next, we use an estimate of the noise floor to generate an adaptive threshold per channel. And finally, our spike detector module identifies 3 key points of a spike. Identifying 3 points allows us to detect not just the presence of a spike, but the shape of a spike as well. This can be extremely important for distinguishing between multiple neurons adjacent to a single channel. Today, I'd like to focus on one of the many optimizations that we've made in our latest chip. This one specifically cutting system power by 15%. Note that neurons spike relatively infrequently, which means that our spike detector spends a lot of time searching for the first point of a spike and very little time searching for the other 2 points of a spike that only occur after the threshold is crossed. We can use this characteristic of the input waveform to reduce memory accesses within the chip by 30%. Let's take a look at how that works. Our spike detector is implemented as a single functional unit that's shared across all channels with an SRAM to buffer the state of each channel. As a sample comes in, its channel state is read from SRAM, an incremental spike detection step is run, and then the updated state is written back to SRAM. Since this is happening 20 million times per second across the implant, each of these accesses add up quite quickly. In our latest chip, we split the state into 2 parts, a hot state and a cold state. The hot state is accessed on every cycle, while the cold state is only accessed once the threshold is crossed, reducing the average access width and saving power. We're also working on a next generation stimulation-focused chip with 4,096 channels still within the footprint of our current chips. In addition to increasing the channel count, we're also increasing the drive voltage so we can get better activation per channel. And to support this higher channel count, as well as a broad range of future applications that you'll soon hear about, we're adding an ARM core onto the chip. And finally, since these chips are the same size as our current chips, we can still put 4 of them together into a single implant for a total of 16,000 channels still within the size of a quarter. As you can see, we've been working very hard to improve the power consumption within the implant. But we've also been working very hard to improve the charging experience of the implant, which Matt will talk about. But first, the robot has just completed inserting all 64 threads. So let's take a look.
Ew.
This is a view of the insertion site, similar to the one that DJ showed you earlier. But instead of the targeting reticles, if you look closely, you can see that all 64 threads, each carrying 16 electrodes, have been inserted into the brain proxy while avoiding vasculature, and all just within the past 20 minutes. Let's hand it over to Matt now to continue the technical deep dive.
Hi, I'm Matt, head of Brain Interfaces Electrical Engineering. Our fully implantable N1 device depends on a battery for continuous operation. When that battery is running low, charging is accomplished through wireless power transfer. However, unlike many consumer electronic devices, which can simply offer a physical connector, charging a fully implantable device poses several unique challenges. First, the system must operate over a wide charging volume without relying on magnets for perfect alignment. The system must be robust to disturbance and complete quickly so as not to be overly burdensome. However, most important is safety. In contact with brain tissue, the outer surface of the implant must not rise more than 2 degrees C. In pursuit of these goals, our charging system has gone through several engineering iterations. The first, if you watched our pig demo in August of 2020, Gertrude was implanted with a version of the N1 charged with our first generation charger. This device was implemented in a small puck package and later separated into a remote coil and battery base. This charger was challenging to use. However, we learned a lot through its implementation. Our current production charger, which charges our current generation of implants, is implemented in an aluminum battery base, which also includes the drive circuitry. A remote coil, 4 times the size of our original device, also disconnectable. This remote coil has increased switching frequency, driving improved coil coupling. This charger is in use today, including several applications within our engineering and animal test facilities. I'd like to show you one of these applications here with a device we call our simple charger. And the coil has been embedded into the habitat. With the addition of one new outer control loop plus a banana smoothie pump, the troop has been trained to charge themselves. So let's see how Pager charges his implant. On the right, we're streaming real-time diagnostics from Pager's N1. When he climbs up and sits below the coil, you can see the charger automatically detect his presence and transition from searching to charging. We see the regulated power output on a scale of 0 to 1 and the current driven into his battery. I mentioned earlier that we improved the coil coupling. However, the high quality factor coils exhibit good charging performance over relatively larger distances, but as they're brought closer to the implant, what you see is a peak splitting effect, where the best, highest efficiency power transfer is pushed up into higher frequencies outside of the ISM band, required for compliance with regulated radiated emissions. In our next generation charger, we address this problem by the introduction of dynamic tuning, shown on the right. This allows us to, in real time, adjust the resonant frequency of the transmit and receive coils so that we can change their properties just ahead of degraded performance. The electrical engineering team is currently engaged in developing a third generation charger. Notable improvements include bidirectional near-field communication. This has allowed us to reduce the control latency and improve the thermal regulation. Improved thermal regulation results in faster charge times. And now, Julian will tell us about how we test the N1.
Thank you very much, Matt. My name is Julian, and I lead the embedded software group on the Brain Instruments team. So when we started building implants, we had a small manufacturing line, and to collect data from an implant, you would manually walk over with your laptop, you would connect, and collect the data of interest. But our goal is to make an ultra-safe and ultra-reliable implant. And so to do this, we scaled up the manufacturing line, our testing throughput, and data collection capabilities. So firstly, we added a large suite of acceptance tests to the manufacturing line. These test the functionality of each component and the final assembly. Implants coming off the line are then subjected to benchtop testing, accelerated lifetime, and animal models. We then collect data from these implants round the clock. This data is processed by a series of cloud workers and displayed in an aggregate manner. And then finally, all of this information feeds back into our design process and empowers our engineers to answer any question about any implant at any time. I'm now going to walk you through different parts of this infrastructure, starting off with firmware testing. So the implant contains a small microprocessor running firmware to manage a whole bunch of its operations. And before we release a firmware update, we want to rigorously test it with both unit and hardware-in-the-loop tests, also known as hill tests. So to do a hill test, what you do is you instrument the battery, you instrument the power rails, the microprocessor, and then we connect to each device with a Bluetooth client. And then we walk the devices through various scenarios to test things like power consumption, real-time performance, security systems, fault recovery mechanisms, a lot of different things. In our original implementation of these systems, we used off-the-shelf components to start automating tests quickly. However, these systems were constructed in a relatively artisan fashion and were very difficult to maintain. And this meant that testing quickly became the bottleneck for development. So to alleviate this, the hardware and software teams developed a new system which integrates all the required components onto a single baseboard. We can then put the charger and implant hardware on individual modules that plug into this baseboard, including one board with opposing coils so that we can test charging performance. This architecture allows us to rapidly iterate different hardware prototypes because we can simply drop them into this system and reuse all the testing infrastructure. Additionally, we can host
good
the
that they
current
did
and
this,
next
but
generation of our
obviously,
neural ASICs onto FPGAs
like-
and plug those into this board as well. And that allows us to test a whole extra layer altogether. So that's how we generated this rather inceptive image here on the right. What you're looking at is spiking activity emitted from some of our simulated neural sensors, streamed through the entire system over Bluetooth, and then displayed on a phone. This allows us to test everything in one system, from chip to cloud. This system is 1/5 the cost, 1/5 the volume, and is very easy to manufacture. This allows every developer to have a personal unit on their desk, and it also allows us to shard the entire test suite over a large number of these units mounted into a rack. All of this has greatly accelerated our rate of development. Let's look next at how we monitor the implant's electronics, the battery, and the enclosure. So the implant will periodically capture all of its vital signs and commit those to flash. And then upon next connection with one of our recording stations, it will stream that data off. So for instance, if we look at humidity, we can get an understanding of the integrity of the implant's enclosure. And by looking at battery voltage and power measurements, we can gauge battery health. All of this is done automatically without any intervention, giving us 24/7 visibility into the quality of every single device. Additionally, we can use this infrastructure to request high fidelity information on demand so that we can investigate different anomalous situations. So for instance, in this particular scenario, we were trying to track down the source of some spurious spikes that we were observing on different channels, and so we requested raw wave samples directly from those channels. Capturing good quality neural signals requires intact, low impedance electrodes. And so this is also something we monitor very closely with dedicated circuitry on the neural sensor. So how do we do this? We do this by first using an onboard DAC to play a test tone on a single channel. And then we record, using our ADCs simultaneously, we record the response signal on both that channel and physically adjacent channels. Not only can we measure the impedance of every channel with this, but we can also map different physical phenomena to different characteristic signatures. So for instance, an open channel will appear as a very large response on the channel, and shorter channels will appear as a large response on neighboring channels. By looking at the purity of the signal coming back, we can also validate that the analog front end of the neural sensor itself is operational. In our original implementation of doing these impedance scans, it took 4 hours to get through all 1,000 channels. But by parallelizing the tests, downsampling, filtering, and then reducing the amount of information we have to stream off the device by moving a lot of the calculation to the firmware side, we're now able to scan all 1,000 channels in just 20 seconds. This means that we can run impedance on every implant every day. And then our internal dashboards can play back a history of this impedance so that we can get a really good quantitative insight into that interface between biology and electronics. Now that you have an idea about how we test and monitor our implants, I'm going to hand it off to Josh, who's going to tell you about how we get feedback even faster by accelerating our implants to failure.
Hello, my name is Joshua Hess, and I'm an engineer on the Brain Interfaces team. We are responsible for the implant system design, as well as many of the manufacturing and testing tools. Julian just talked to you a little bit about some of the ways in which we test our implant electronics hardware and software. But what about the entire system as it relates to longevity in tissue? One of the ways we've addressed this is with the development of our in-house accelerated lifetime testing system. The system allows us to expedite and capture long-duration implant failure modes at scale to rapidly increase our pace of iteration. Even better, the system also significantly reduces the amount of tests which require animal models, both for implant prototypes and, of course, longevity testing. So how does the system work? Well, at a very basic level, it comes down to 3 things. First, we want to mimic the internal chemistry of tissue. Next, we want to accelerate these chemical interactions, as well as diffusion with our implant materials. And finally, we want to aggressively cycle the internal electronics of our implant. With these things, primarily the first 2, we've achieved a conservative 4x acceleration by the Arrhenius relationship. In other words, every day our implants spend in our accelerated system is equivalent to at least 4 days spent in vivo. Historically, one of our greatest challenges has been the battle against moisture ingress into our implants. So we continuously monitor the internal humidity to watch for abnormal rise. Here, in white, you can see some internal humidity data from implants in some of our animals for the duration of over 1 year. As you can see, our internal humidity sensing is so sensitive, it can even detect the very small and slow humidity rise just from diffusion through our implant materials. Now, in blue, you can see that same internal humidity data, but from devices in our accelerated system. Now, if we adjust this data for our acceleration factor, you can begin to see not only the agreement in this data, but also just how far into the future this data extends. Now, in red, you can see a device which has failed in our accelerated system. This device showed an abnormal increase in humidity over the duration of many months before implant electronic failures occurred. So how did we build this system? Well, we started building the first system prototype just after the COVID shutdown had begun in early 2020. So we had to get a little creative. As you can see, our first system prototype was a little scrappy and operated out of one of our apartments, as indicated by the carpeting. Although scrappy, the system allowed us the fastest path to start testing our devices, tuning our working fluid chemistry, and checking our constraints. We also immediately started root causing observed failures in early implant prototypes, fed that information into the next prototype designs, and literally rinsed and repeated. Over the duration of just a few months, the system was built out totally custom and highly iterated with 2 system versions and countless minor iterations, leading us to our currently operated 3rd generation system, which achieves high density testing with automatic in-vessel charging as well as automatic data collection. The system also features an implant sled assembly, which accepts brain proxy material such that the implant can be installed and inserted by the surgical robot, just like you saw a few minutes ago. We also integrated the system into a high-density rack mount form factor, along with a centralized fluid management system, both for chemical uniformity across vessels and also reduced operational maintenance. The system has been in operation for the last 1.5 years and has had its fair share of challenges. Since the system itself is undergoing the same accelerated abuse as the implants within it, it has been extremely challenging to design, build, and maintain a system of this scale while keeping it robust, even against itself. So what comes next? Well, we have started work on our 4th generation system and have totally redesigned it from the ground up to be a hot swappable, single implant per vessel design, partly inspired by high-density compute servers. With this new system, we will achieve a whole new level of density, robustness, and scale. We also intend to have many of these systems operational in the pursuit of capturing even the lowest frequency case failure rate. With this, we will have thousands of implants tested in pursuit of these goals. We've already started work building out this system, but there is still a lot left to do. There are also many exciting challenges ahead of us, such as introducing mechanical stressing, brain proxy micromotion, and even replicating tissue growth around the threads for more complete and representative accelerated testing. So now that you've heard some of the ways in which we rigorously test our implant designs before production for surgery, Christine is now going to take you through a detailed look at our surgical process.
Thanks, Josh. Hi, everyone. I'm Christine, lead of the surgery engineering team.
He was calling her Christina.
To get an N1 device, it's essentially these steps: targeting and the incision, drill the craniectomy, remove the tough outer meningeal layer called the dura, then insert the thin, flexible threads of electrodes, place the implant into the hole we created, and then that's it. You've got an implant under the skin. Look, Ma, no wires. Just kidding. I mean, seriously, no wires, but I don't actually have one. The surgical robot does the thread insertion part of the surgery. This is because it would be very difficult to do manually. Imagine taking a hair from your head and trying to stick it into Jell-O covered by Saran wrap, and doing this at a precise depth and position, and doing this 64 times within a reasonable amount of time. And a neurosurgeon would probably not like it very much if we asked them to do this for the surgery. So we have the robot that you saw doing its tiny dance. I sort of wanted to call it Tiny Dancer, but it's called R1, which is also great. The rest of the surgery is done by the neurosurgeon. In order for us to make an accessible and affordable procedure, we need to revisit this. I'll tell you why. When I was in school, my dad lost the ability to walk and to use his arms and even to speak. He was diagnosed with ALS. We would look on the internet and you could see maybe one person here or there who had some cool custom robotic assistive device, but it was deeply frustrating how limited were the options available to him. And there's hundreds of thousands of people with paresis, not even counting people with other conditions that our device might be able to help. Meanwhile, there's not that many neurosurgeons, maybe about 10 per million people. And it takes about a decade or more to train a neurosurgeon. They're already generally very busy. And you can imagine
But I
it's
think
very
we're doing
expensive.
this task.
In order for us to do this good and have an affordable and accessible procedure, we need to figure out how one neurosurgeon could oversee multiple procedures at the same time. This might sound sort of crazy, but probably so did laser eye surgery before LASIK. LASIK's been around for about 30 years. In the beginning, the laser robot did just the most fundamental core part that it had to do, and the surgeon did the rest. And over the iterations, the surgeon has to do less and less, and the laser robot does most of it. And it's a highly compelling procedure. It takes just a handful of minutes and often gives life-changing results. Since I joined in 2017, we've also done a handful of iterations to optimize the thread insertions of the robot. One of the challenges that we've had to face has to do with the optomechanical packaging. So as you can see here, there's about 3 primary optical paths that are really valuable for us to have reliable thread insertions. One is the visible imaging of the needle inserting the thread. And then another is the laser interferometry system called OCT, optical coherence tomography, that gives us the precise position of the brain while it's moving in real time. And then also we have to provide lighting and illumination to see what's going on in the visible light camera. And doing all this where the needle is at the bottom of the craniectomy, especially when it's close to the skull wall, can be pretty difficult to fit everything and be able to see it. So the way that the team solved this is by putting all 3 of these optical paths into one optical stack using photon magic or polarization, whatever you want to call it. And that enables us to do vessel avoidance in real time. So as I mentioned, the brain is moving, and where we place targets in the beginning may not be where you want to insert at the moment the needle is going down there. So the robot can actually detect the vessels and then determine if we're going to insert onto a vessel or not, if it's safe to insert, and then that way we can avoid inserting onto major vessels. And that brings us to the robot that we have here today. There's still a lot for us to do to get to that procedure where we reduce the role of the neurosurgeon and make it affordable and accessible. The 2 elements of the surgery that demand the most skills from the neurosurgeon are the craniectomy and the directomy. Alex and Sam are going to tell you a bit more about how we think we can get rid of the directomy step. So that leaves the craniectomy. In neurosurgery, if your craniectomy is small enough, you can use a standard tool called a perforator, which makes quick work of this job. But for a larger craniectomy, the surgeon has to rely on their skill in order to accommodate the variability patient to patient in skull thickness, skull hardness. Even within the same patient, in the same craniectomy, you can have different skull thicknesses, for example. In addition, if we can make something that has a very high precision craniectomy, we can open the design space for future ways of mounting the implant to the skull. So I'll show you a few of our prototypes.
Oh, no.
Ultrasonic cutters, like what's on the screen, and oscillating cutters have the benefit of not cutting soft tissue. You can cut the bone and not the brain. But however, as you can see here, our ultrasonic cutter prototype created quite a bit of heat to cut at the rate that we wanted. So onto the oscillating saw. Here, we designed a blade to minimize cut time and also conducted sound and also heating. And as you can see, you can cut through hard things like bone, but not soft things like skin. It's simple and it works. However, if you wanted to cut an arbitrary depth or arbitrary shape, the oscillating saw just won't cut it. I was afraid no one would get it. You guys are smart. There's a time-tested solution for drilling arbitrary shapes, which is a CNC drill. The challenge with us doing this on a person is that we need to make sure it cuts reliably every single time, doesn't cut too deep. And a few ways that we're using feedback to make sure we don't cut through the brain are force feedback and also impedance. And if I could get a volunteer, no, just kidding. Maybe next time. But yeah, so this is some insight into some of the things we're working on to make an accessible and affordable procedure. And now Alex is going to tell you a bit about our next generation developments.
Thanks, Christine. I'm Alex. I'm a mechanical engineer here on the robotics team. Now that we've covered the technology and surgical process for our current device, we'd like to cover some of our next generation development projects. I and the next couple speakers would like to talk about one of those projects, which is enabling device upgradability. You've gotten to hear about the advancements we've made over the past year. We've improved implant robustness, battery and charging performance, Bluetooth usability. Realistically, every new device version is going to be significantly better. It'll be more functional, it'll last longer. We need to keep this new technology accessible for our early adopters. This means that we need a solution to make device upgrade or replacement just as easy as it is to initially install. As many medical device companies have found, this is a challenging problem. The body's healing response doesn't make this easy, so this isn't solved yet. But we've made significant progress towards enabling this that we'd like to cover today. Now, we'll have to start with some background as to what makes device upgrade challenging. And we'll start with the anatomy. Under the skin, you have the skull. Below that, the dura, a tough membrane that separates the bone from the brain. And between the dura and the brain, you have the pia-arachnoid complex, a fluid-filled suspension for the brain. To install the device, the surgeon removes a disc of skull and dura to expose the brain surface. The device then replaces the removed material. The challenge is here at this interface. Over months, all empty volume is filled by tissue, encapsulating the device and the threads. The device would be trivially easy to remove. Because of the thread's small size, they would slip right out of the brain. It's the tissue layer that forms above the surface that makes the removal challenging. We've built tools in-house to study this response and characterize it, such as histology and micro-CT. In these images, you can see that layer of tissue that has formed above the surface, encapsulating the threads and adhering to the surrounding tissue. We've explored many different avenues for designing around this healing process and finding a solution to make device upgrade seamless. Our best successes have come from making the procedure less invasive. Instead of directly exposing the brain's surface, we instead keep the dura in place, maintaining the body's natural protective barrier. This prevents encapsulation at the brain's surface. And really, this is actually a huge win for making the surgery simpler and safer, as Christine alluded to. However, this doesn't come for free. The dura is a very tough, opaque membrane. As you can see in these SEM images, it's composed of a dense network of collagen fibers. These offer an array of technical challenges for inserting our electrodes. One of those challenges is imaging through the dura. As you can see on the left, our current custom optical systems offer pretty incredible capabilities for imaging the exposed brain surface. However, as you can see on the right, once the dura is in place, you can't see the dense vasculature at the brain surface. The dura is in the way. There's simply too much attenuation. To solve this problem, we're developing a new optical system that uses a medical standard fluorescent dye to image vessels underneath the tissue. Here, you can see that dye perfusing through the vessels, highlighting them. There's still a lot of engineering work to go to prove accuracy and repeatability of this system. But once that's done, this will allow us to target and avoid blood vessels underneath the dura. We're also exploring applying our laser imaging system to deeper tissue structures. In the bottom left, you can see a section of the tissue layers underneath the dura. This image is compiled from multiple volumes from our optical coherence tomography system. You can see the collage of those volumes above. In the future, these new systems, when combined with correlation to pre-op imaging, such as MRI, will enable precise targeting without directly exposing the brain surface. Now, imaging isn't the only challenge that comes with the tough dural anatomy. Now, I'd like to hand it over to Sam to talk about some of the challenges of inserting our electrodes through this membrane.
Thanks, Alex. Hey, I'm Sam, and I lead the needle manufacturing and design team. So, as Alex mentioned, the same properties of the dura that make it a good protector of the brain also can be really certain threads. In humans, the dura can be over 1 millimeter in thickness. It doesn't sound like a lot, but compared to our 40 micron needles, it actually is a lot. For example, if you scaled up the needles to the size of a pencil, the dura would scale to over 4 inches in thickness. Take a look at how far you have to zoom in to even see it. By the time the features of the needle come into frame, you could see individual red blood cells in the same frame. This is just wait. This is a real-life SEM image of our latest design. On the left there, you can see the end of the thread. In the middle is the needle, and on the right is actually a piece of my hair. So yeah, it's extremely small. And besides being really small, there's a lot of other challenges associated with designing this. One challenge is that we have to use the needle and the protective cannula that it sits in to grab onto the thread and to hold it while we peel it from this protective silicon backing. And then we have to keep holding it while we bring it over to the surface and then release it from the cannula during insertions. Another challenge is that the brain is really soft beneath the tough dura. And so if the needle isn't sharp enough, it'll just keep dimpling the surface without puncturing. And if this free length gets too long, it can actually just buckle the needle like this. Another challenge is that we don't just have to get the needle through, we have to get the thread through as well. So we really have to focus on optimizing the combined profile of the needle and thread together. And these are just some of the challenges associated with designing something like this. And so far we found that the key to solving this problem has been improving on our speed of iteration. But let's look at how we make these things in the first place. So we start with a length of 40 micron wire made out of tungsten and alloyed with a little bit of rhenium for added ductility. We designed this femtosecond laser mill in-house to cut the features of the needle and cannula. And it can do this with sub-micron precision. We spent a lot of time this year turning this thing from a science project into an industrial system. Just a couple months ago, it took a skilled operator 22 minutes to make a needle. And even a skilled operator could only get about 58% yield. Today, that same process takes just 6 minutes, and anyone can get 91% yield with just a few minutes of training. With only one click, the mill cuts and measures the needle and cannula and uploads the measurements to our limb system so that the robots can use the exact dimensions for each needle that it uses. Now, this is all for our current design, though, and we've had a couple years to optimize the manufacturing process of it. The current design has served us well so far, but it doesn't quite protect the thread well enough to get through the tough dura. So, like I said, we had to come up with something new, and we needed to be able to iterate on designs quickly. Unsurprisingly, there's no page in machinery's handbook for this kind of thing, so we dug into the science of femtosecond laser ablation and figured out a workflow that allows us to use our laser mill much like a CNC mill. This allows us to iterate several times. This allows us to iterate in under an hour for new designs, allowing several iterations per day when we're really on a roll. As a result, the latest design, seen on the right, can actually insert through 9 layers of dura, totaling 3 millimeters on the bench top. This is far more than we could ever expect in a human with significant margin. The needle isn't the only part of the puzzle, though. As you can imagine, all of these designs here work with different threads. So we need a way to iterate on that as well. And we do this by having our microfabrication process here in-house. This summer, we completely rebuilt our clean room in about 9 weeks, which, among other things, greatly reduced particulate counts, which allows yield and throughput to greatly increase. This, combined with all the other great improvements the microfab team has made, allows us to iterate on new designs in just a matter of days. The last piece of the puzzle, though, is testing. We can come up with as many new designs as we want, but unless we have a way to actually test them in the right conditions, we won't know what to tweak. Or even worse, we'll spend time optimizing for the wrong things. Take this failure mode, for example. A few months ago, we got to the point where we could pretty reliably insert through the Dura. But when we took the proxies and put them in our micro CT imaging, we realized that our hold on the end of the threads was actually too strong, and we were pulling them out just a little bit underneath the surface. By the time we solved the problem, we realized that this issue was very sensitive to the properties of the surrounding material or tissue. We could make a proxy where this never happens, and we could make another proxy where this happened every single time. And this highlights why it's crucial that we spend time making our benchtop tests match tissue as accurately as possible. And I'm going to pass it off to Leslie now, who's going to talk about how we've been doing that. Thanks.
Hi, I'm Leslie, and I lead microfabrication R&D. And part of what we're interested in is understanding the biological environment our implant and threads experience once they're fully installed in the body. Learning directly from biology, though, is inherently slow. So in order to move fast, we're developing synthetic materials that mimic the biological environment. This allows us to learn as much as we can on benchtop and start taking steps away from the industry standard of animal testing. Developing accurate proxies, though, is challenging. The implant environment is made up of many anatomical layers that all have unique properties. And as time goes on and the implant site heals, new tissue forms, filling any available space. In addition to that, motion related to cardiovascular activity and head movement introduce added complexity. So to start addressing some of these challenges, we're engineering materials using feedback from biology. This may involve mechanical characterization of tissue or analysis of interactions at thread-tissue interfaces. Much of this characterization is even done during surgery itself by using custom hardware and software that modifies our surgical robot to double up as a sensitive characterization tool. We then use the data collected and feed it back into optimizing our materials so that they behave mechanically, chemically, and as shown here.
So I'm realizing now that the barred motion actually removes, it does a first pass where it adds moves and then it removes them sometimes, and that's causing this problem. And I'm deciding that this whole thing about having this be an array that's parallel is, it's going to be annoying. Even once I get it working here, it's going to be annoying to maintain. So I'm just going to change it to a hash table because we know what transaction it's in. And we know the ID. I think if we do by ID and move type, we can just make it be a hash table. So that's what I'm going to do.
We have a super long wish list for our proxy of the future, but some of those items include a surgery proxy with integrated soft tissue, brain, bone, skin, or even a whole body. A brain proxy that simulates motion, vasculature, and electrophysiological activity, and a biological proxy to test biocompatibility and electrical stimulation. There's a ton of ongoing work getting us closer to our proxy of the future, including work on lab-grown cerebral organoids, as shown here. And all of this will get us closer to a future where we learn more and iterate faster on benchtop and reduce our reliance on animal models, or even one day replace them completely. And with that, I'll hand it over to Dan, who will be presenting a very exciting next generation application. Thank you.
Wow, she hardly said anything. All right.
Thank you, Leslie. My name's Dan, and I came to work at Neuralink after following a career in visual neuroscience research. I was inspired to join this company because I saw in our device the potential to restore vision to people rendered blind by eye injury or disease. There are a number of particular characteristics of our device that make it uniquely suited to this application. Firstly, as well as being able to record from every channel, we can stimulate neural activity in the brain by injecting current through every channel. This is important because it allows us to bypass the eye and generate a visual image in the brain directly. Secondly, our device can have an enormous number of electrodes, for a visual prosthesis, this is important because the more electrodes you can have, the higher density of an image you can create in the brain. Thirdly, thanks to our robot, we can insert these electrodes deeply into the brain. Now, this is an important thing for a visual prosthesis because the human visual cortex is buried deeply in a fold in the medial face of the brain called the calcarine sulcus. In this image, I've highlighted the calcarine sulcus in red in an MRI. It contains a map of the visual world, the visual field.
New future.
It's about a surface area equal to a credit card on each side. And if you unfold it and flatten it, you see that the image is inverted, it's upside down. But more interestingly, it's distorted so that the central part of the visual field, the fixation point, is greatly magnified. So for example, if you look at this image of Lincoln, if you look directly into his right eye, everything to the left of that fixation point is directed to your right visual cortex, and everything to the right goes to your left visual cortex. His eye, even though it's very small in the image, is magnified in the brain to occupy nearly a quarter of the surface area of the visual cortex. Over the last half century, visual neuroscientists have developed a profound understanding of visual processing in the brain. What's driven most of this research is recording from single cells in the cortex, usually of macaque monkeys. One of the seminal discoveries was that every cell in the visual cortex represents only a tiny part of the visual field. Your perception is made up of a mosaic of tiny receptive fields, each belonging to a single cell in your visual cortex. So if you record from one of these cells in a monkey, say in this location, you can find a very tiny region of the screen where a light stimulus will cause modulation of that neuron. Another location in visual cortex will have a location elsewhere on the screen, in this case in the lower visual field. These regions are called receptive fields. We've inserted our device into the visual cortex of 2 rhesus monkeys, whose names are Code and Dash. That means we can record activity from their visual cortex generated by their normal home environment as they roam around. But as we all know, monkeys love banana smoothie. That means we can easily teach them to fixate points on a screen and reward them. We can reward them very precisely because we can track the location of their eye using an infrared camera. One of the things this allows us to do is to plot the receptive fields for every neuron that we can record with a single device. Now, we do this by showing the animal a movie of random checkerboards whilst he fixates steadily on the screen. Then we take only the frames of the movie that generated a response in the cell and average them all together. This is a technique known as reverse correlation. It's generally used quite widely in visual neuroscience for this purpose. And this is an example of a receptive field plotted with this technique. The central cross is the fixation point, and you can see the little red and blue regions of excitatory and inhibitory receptive field. These regions give cortical cells some of their characteristic properties. So we can record all the receptive fields from all the electrodes at the same time. And if we take all these receptive fields and accumulate them together, overlap them, and place them on a computer monitor for scale at a typical viewing distance, you begin to get an idea of how much of the visual field we can cover with this preliminary device. Many of the receptive fields are close to the fovea, close to the fixation point. That's partly due to the magnification that I talked about of the fovea. But there's also a scattering of fields in the periphery. These are from recording sites deeper in the brain in the calcarine sulcus. So far, I've only talked about recording information from the cortex. But to produce a visual prosthesis, we need to stimulate. So if we stimulated the cells whose receptive fields are in this location, we would produce a perception of a flash in that location that only the monkey can see. How do we know that the monkey sees it? How do we know what it looks like? Well, unfortunately, we can't ask them what they see, but we can train them to tell us something about that phosphine. We start by training the monkey to fixate a central point on the screen, like this white dot, and we start by presenting real visual stimuli on the screen and rewarding the monkey for making eye movements toward those stimuli. So here we flash a white dot, and the monkey makes an eye movement towards it, symbolized by the green arrow. We then choose another random location and reward the monkey for making an eye movement towards it. Once he's got good at this task, we can begin to interleave these real stimuli with electrical stimulation of electrodes and produce a phosphine. The monkey sees the flash and naturally makes a saccade towards it. This tells us not only where in the visual field the flash occurred, but we can also change the current that we inject in that electrode to see how often he makes that saccade, how noticeable or how big perhaps the stimulation, the phosphine is that we're producing. Let's look at code performing this task. I want to show you first at 1/4 speed. There's a visual flash, and he makes an eye movement towards it. The monkey can only see what is white on this screen. He can't see his own eye movement, and he certainly can't see when we stimulate. But here we stimulate, and he makes the same saccade to the same location because we stimulated the same electrode. Nothing appears on the screen at that time, and he has no other cue to make that eye movement. Let me show you this in real time. You can see monkeys like to work very quickly. And when we stimulate, he makes that saccade in real time. And looks like he's had enough. So what I've shown you is a way to produce a phosphine in the visual field. This is not something new in visual neuroscience, but if you think about that phosphine as a single pixel in a visual image, all we need to do is scale up and produce a great many more pixels and have them covering the visual field. This is a schematic of what a visual prosthesis using our N1 device might look like. A camera, the output from a camera would be processed by an iPhone, for example, which would then stream the data to the device, and the image would be converted into a pattern of stimulation of the electrodes into visual cortex. With 1,000 electrodes, we might be able to produce an image resembling something that you see there on the right. But as Avinash told you, our next generation of the device will have 16,000 electrodes. If you put a device on both sides of your visual cortex, that would give you 32,000 points of light to make an image in someone who's blind. Our goal will be to turn the lights on for someone who's spent decades living in the dark. Thanks very much. I'll pass you over to Joey, who's now going to talk about another very exciting application of our device.
Thank you, Dan. So my name is Joey. I'm a neuroengineer, and I'm the head for the next-gen team at Neuralink. So for persons with spinal cord injury, the connection between the brain and the body is severed. The brain continues functioning normally, but it's unable to communicate with the outside world. You've already heard about how we can use the N1 link as a communication prosthesis to help someone with spinal cord injury control a computer or a phone, but it can also be used to reanimate the body. Let me show you how. First, a little neuroanatomy. Movement intentions arise in motor cortex and are sent down long nerve fibers through the spinal cord. These are upper motor neurons. In the spinal cord, they synapse, that is, make a connection with another motor neuron, a lower motor neuron, which sends these movement intentions to the muscles, which contract, and in turn, you have movement. While, of course, there are many other circuits involved in voluntary movement, you can think about the spinal cord as many pairs of these two connections. And in spinal cord injury, one of these connections is severed, unable to make the muscles contract. Let's zoom a little bit further. So here you can see on the left a cross-section of the spinal cord with a fiber coming down schematically. This travels through the white matter tracts. This is the upper motor neuron. And then it synapses within this butterfly-shaped region of gray matter in what's known as a motor pool. In the motor pool, the lower motor neuron descends out the ventral roots to the muscles, which contract. And then the sensory consequences of those movements, for example, the touch of your hand against an object, return to the spinal cord through the dorsal roots and ascend the spinal cord up into the sensory regions of the brain. Again, in spinal cord injury, this connection is severed. If we could place electrodes into the spinal cord, say in a motor pool adjacent to lower motor neurons, we could stimulate those neurons, activating them, and in turn causing the muscle to contract and movement to occur. But this is very hard to do. The spinal cord is quite delicate, and it moves significantly within the bony spinal canal. This could cause damage to the electrode, it could cause damage to tissue, or both. But our electrodes are small and flexible, and our robot is able to insert them deep into tissue, perhaps all the way down into the ventral horn of the spinal cord. And so we have done just that. Here you can see a view from the R1 robot. It's a targeting view, and we've placed electrodes across many millimeters of the spinal cord. And the R1 robot is able to insert those electrodes deep into the ventral horn, into motor pools, in very close proximity to lower motor neurons. This is important because it allows them to have a localized connection to those neurons and activate very precise movements. Now, to track movement, it's very common to use motion capture markers, like you might see in the production of a movie. These can be placed with a light adhesive, and you can see me placing these on my hand. We're going to use these markers to let us zoom in on movement in the next couple of slides. Okay, so here's a pig walking on a treadmill, and you may have seen something like this before in a previous Neuralink presentation. But unlike before, this pig has more than one Neuralink device. There's a device in the brain, but there's also one in the spinal cord. And we can stream neural data from this device, these devices, in real time and use them to do things like decode the movement of the joints of the pig. So here you can see on the left a time series of the hip, knee, and ankle, and we're decoding those movements. So this is super cool, but that's actually not what we want to do. We want to go in the other direction. We would like to stimulate the spinal cord and cause movement to occur. Okay, so let's do that. So here's a pig, a happy and healthy pig doing what pigs like to do, which is root around for food and snacks. And as you'll see on the floor, there's a blue square. This is a voluntary engagement zone where the pig places itself, indicating that it's comfortable to receive stimulation. When it's in this zone, we stimulate, and if the pig leaves this zone, we'll stop stimulating. And as before, you can see we're able to track the position of the joints and also stream neural data as well. Okay, so let's stimulate an electrode. So here's one electrode on one thread that when we stimulate causes a flexion movement of the leg. So on the left, you can see the movement of the joints, and you can also see the time series of the stimulation pattern in yellow. So the leg is moving up. Here's another electrode, which when we stimulate causes an extensor movement. This is actually a little harder to see because the leg is straightening and the hips are shifting, but if you look carefully, you can see how the leg is moving. We can stimulate on a great variety of threads and produce different movements and actually sequence them spatial-temporally to provide patterns. So on the left, you can see a time series of different stimulation on different electrodes. You can see the movements of the joints. And on the right, we're zooming in on muscle activity that gives us an idea of the kind of strength and power and specificity of those movements as well. So in addition to doing sequences, we can also achieve sustained movement. These are powerful muscle contractions of the sort that you might need for standing or other load-bearing activities and are really crucial for interacting through the world. Okay, so stimulating the spinal cord is only one piece of the story. You also have to get command signals for the stimulation of the spinal cord. Unfortunately, we have a way to do that. We have the N1 link that you've already heard about placed in motor cortex. How would that work? So we place threads in motor cortex and record spikes. These spikes would be wirelessly transmitted in real time and decoded into patterns of stimulation. Stimulation would then be delivered to the ventral horn of the spinal cord, to the appropriate motor pool for the muscles that we'd like to activate. We then stimulate, activate those lower motor neurons, which causes the muscles to contract and movement to occur. Now, of course, movement without sensation is actually kind of difficult. Just think about what it would be like to try to move your limbs if they're numb. But we can also get sensory information as well. So the sensory consequences of your movement can be recorded in the dorsal horn of the spinal cord in the form of spikes. For example, here, a feather touching the hand. These spikes can in turn be decoded in real time, sent to patterns of stimulation to either the same N1 device in the brain or perhaps a different one in a sensory area. Stimulation of that part of the brain would cause percepts of touch and proprioception, closing the loop. So putting those two loops together, we have motor intentions decoded from the brain, used to stimulate the spinal cord, causing movement, and then the sensory consequences of those actions being recorded in the spinal cord to stimulate the brain, causing perception. Now, we have a lot of work to do to achieve this full vision, but I hope you can see how the pieces are all there to achieve this. And if you find this prospect as exciting to you as it is to me, I hope you'll consider joining us here at Neuralink. Thank you.
We're putting the team on, and then we'll do some Q&A.
All right. We learned about the things. And now we learn why programming while half paying attention to another thing is not the best way to program. So I'm a little bit annoyed. I think someone changed assert so that it logs, but like this assert is not frickin' going off. Now it's not that hard to fix. I just didn't change that part, but like still I need assertions to break at the assertion point. So I'm going to be emailing somebody and saying, "Hey, can we fix that?" All right. So new charm setup, that's no longer a thing. Hey, look, nobody sets it. What a surprise. Wait, I already do this, right? I did this for e-single. That's online 2025. It's a different e-single. All right. I passed a pointer where I shouldn't have done that. Shouldn't have done that. All right. Fuck, it doesn't work. I mean, the rest of it is working. But the part about the jump animation is not working. That's also kind of not working. What about SIG? Okay, SIG 90 works. So like the actual functionality of the thingers works, mostly. This is kind of wrong, though. Why is SIG 90... Wait, what? recorded this when it was kind of wrong. Like, I don't know why those are getting blocked. They should be. This should shift from a left triangle to a right triangle. That time it worked. Oh no. Okay, well that's something to debug. Probably tomorrow because it's at night. Not good. It could be something that I just introduced. Something else. So I really only want one finder add. I feel like this would have gone a lot better if I had just done the final correct thing in the first pass rather than doing it wrong a bunch of times. See, this sets E single here. I don't think we actually need this one. We're gonna have to diff this code against the old code and like see what we think. This is well, maybe I go to 690s. That's broken. Whoa. That is broken. Rockin' like dockin'. Time it worked. Great. Great. Game's so loud now. Will you guys just stop it? I can't handle it. Jesus. Okay. There is a problem. Let's look over, since we did a bunch of spam and things, let's look over and just be sure that at least it plausibly looks like the code that's there now. Roughly corresponds. So we don't need this single index anymore even. Let's just delete that. We're just, every time we see something, you know what? We don't need this. That's gone. We're going to go back here. We're going to get rid of it from, going to get rid of it from here. We're going to get rid of it. We're just getting rid of it. Many people would not do this. We do this. We do this. All right. Right. We do this. Okay. Load the changes, please. All right. So before we said we look at the charm setup on the single move. If that's got move infos, etc. Now we say if t is equal to transaction. That is new, but that part worked for a while. At least I think so. We were cowabungaing in here, so we know that that part worked. Then we do this lookup. Now I wonder if we change the move type. We could just do it by ID, honestly. Like, I don't even know. I don't feel like we even need the move type. You know what we're going to do? That's all. Be single. Make sure. There might be a thing where I typoed that because there's 2 in scope, but no. All right. I lowered my voice instead. Will you guys stop fucking complaining about everything? Jesus. Like, it's my least favorite part of streaming. Okay. Hey, look. It works now. So, yeah, my theory is I remember, actually, we change the move type between charmed and other things sometimes. So, yeah. Yeah. GG's. The ending code ended up being very, very simple. Now, is SIC90 still broken? Apparently, SIC90 is still broken. What is going on? If C setup. Bro. Okay. Well, this would explain why it's messed up sometimes. This is confusing though, because we add it by value. And at the top of try move clones, we do a table reset. You know what? Fuck even the temporary storage part of it. We don't even care about that. Because that's maybe vulnerable to some kind. It's almost never a problem, but I'm just trying to... God, this is so fucking annoying. I need to be able to turn off mini dumps locally. Okay. So. Okay, well maybe that was related, because... Oh wait, that was on SIC90, not here. SIC90. So what we could do is run in a more serious memory debug mode. I mean, this is working better now. So it's possible... I don't see any temporary storage mark kind of a thing. But it's possible that something bad was happening there. I'll have to investigate that later, but this all looks like it's working fine now. So that was the problem. We can investigate that later with like a very serious allocator. I don't remember how to solve this level. Let's have fun solving the level for a second. Oh yes, so... Oops, no, don't do that. Go there. Go there, okay. And then... We can leave that guy there. Oh no, we can't. You have to go here and go there, and go there, and go there. That's a SIC90, dude. And then we go there, there, and then that guy goes out. SIC90. SIC90, okay. Well, let's try some of these other levels in this set. What's this one called? It's also one of my barred triangle. Yeah, so this is just demonstrating this. So that's fine. this one is removed for now. So that's SIC 90 again. This is this guy. Zach didn't like this level for some reason. I think it's fucking awesome. Zach hates all my levels. I don't know what his problem is. Is this I-beam? Why is it named SIC 90? Because you do a SIC 90. Like, bro, how can you even ask this? Let me play. Actually, let's do this one. Let me see if I can remember how to solve it. I mean, I kind of can't do anything here. Dude, I don't remember how to do anything on this level. I mean, obviously it's solvable. Dude, that's so neat. Why does Zach have this one turned off? I would like to know. Okay, I must have to. Dude, how do I solve my level? Can't even right now. Well, you do a 180 in the beginning, but 180s are easier than 90s. Everyone knows that a SIC 180 is like way easier than a SIC 90. All right? Let's just be clear about that. How would I solve this frickin' level? Does the bard go down to move the rocks? You know, that's a good point. She probably does. She probably does. I wasn't even thinking about that. I was like, oh, I bet that's the trick. No, she probably is fine down here now. Right, okay, the thing is, she needs to stay spaced out from the dudes. All right. So like if I want to push the yellows, I need a little bit That's not quite what I need. Let's hold on. So there we go. Okay. Now there's a spare one. Wait. It's broken, that's why. Dang it, dude. So the idea was supposed to be, well, maybe it's not broken because maybe I can't win now? Oh, I can. Okay. Level's totally broken. The idea is supposed to be that the warrior has to walk all the way to the other side of the level and back. And that doesn't work. I'm kind of not sure. So let me see. Actually, Zach went through and put design notes in a bunch of things. Let me see if there is one here. Nope. Nope. I assume it's because of the exploit. But I think this is fixable because I'm not sure why. Let me look at my solution because I'm not sure why I made that the warrior. If it's someone who can't push, then it's just fixed. Let's see. So you'll see what the solution is. It's a cool thing where the bard... Wait, what? Oh, I have extra blocks. That's why. But yeah, it doesn't have to be someone who could push at all. But this is the thing is, it's a little bit unnecessary because you see on each side here we have one extra. So like I could redesign the level with the exact number of blocks. I'm not sure why I did it this way. Maybe it was to have 3 stacks everywhere. 3 stacks like slee stacks. Let's just try it really fast. Like, what's the solution that I did? So you get a 3, you go there. You get a 3, you go there. I mean, the thing about getting the middle is nice. And how symmetric it is. Okay, you could do a similar thing like this. If it were like this. Okay, like I go over here, I go shoop, 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 no. Shoop, 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 shoop de whoop. Okay, now the warrior cannot walk across anyway. This is what it's supposed to be. And then you slot in and then he goes. Oop. Lol. It's not as pretty that way. So I feel like I should make the level bigger by 1. And then we could, by 2. Right? I mean, maybe I just tried to shrinkle-a-dink. I tried to shrinky-dink it. Right? Actually, yeah. Let's just do this manually. One, 2. Go ahead and do a 3rd. And Cam Newton, and then do this. That looks uglier, kinda, but like, boop, boop. Oh no, because I moved him closer. Boom. Boom. But it looks nicer in some ways because of the layout of the stones on the level now. Boop. 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 He cannot cross. But now, oops. Oh. Now he can. No, no, don't go. Don't go crazy. I think that's nice, sir. It at least is not exploitable. Why make him go back? Because designed video games, bro. Design video games. Design. It's design. It's called design. Can make it 2 wider, 1 column on the other side of the center. I mean, I think you posted that before I did it, but yeah, that's what I did. Is the blue pad glitching? I mean, it's probably sticking into the floor. Yeah, it's Z fighting with the floor, but that's not a big deal because final art will not be like this. Now, is it exploitable? So the question is, can the warrior frickin' do something else anyway? Like, maybe the warrior can, like, maybe you can just do something really messy, right? So one thing that I'm thinking is maybe I should make it impossible for the warrior to cross the middle. Because, like, I mean, once I get this, right? Oops. Once I get this, then oops, let me put him there. I don't know, maybe it's not exploitable. Like, I'm trying to think of a way. See, the thing is, there's no way to bump against anything. Oh, here we go, right? Okay, see this? Uh-huh. Uh-huh. So maybe the level is as follows. Okay. The level is as follows. There's a wall back here. There is a there's a tunnel here. Okay. And there's a, what is going on? There's a really mean dragon. Oh, that's the other level. There's a really mean dragon who lives back here. Okay, well, she's starting in the wrong place, so let's fix that scenario. Oh, right. I mean, we sort of want her to be able to start up here and have, I don't know, maybe it doesn't freaking matter. Let's just have her start there. It's fine. Because she can just get down clean. And that gets rid of any question about, am I supposed to move that before I go down? It's like, no, you just go down. And this guy cannot get past the very mean dragon. And the thing is, in order to open the yellow gates to get him out, you need to have all the stones on the ground. Okay. Which means you can't really block the dragon that way. Now, however, maybe you could do some bullshit, and you probably can, I don't know, where, right? So this is scary because now we have too high, right? And in fact, maybe we can do some crap where like you could imagine trying to pile up some of this stuff. Although this would be very hard to transport across the level. You know what? For avoidance of doubt, I don't even care. I'm just going to make extra sure that nobody can screw with my scenario. All right? Now it's like, lol, you can't even get across. And then let's even, yeah. Anyway. Now exploit this damn level. I didn't finish the exploit. It was much cleaner. Am I sure there was an exploit? Well, here's the thing. There's two classes of wait, what was much cleaner? You mean the very original that had fewer buttons? Yes, that was, I totally did exploit it. Without the dragon and wall. Yeah, that was busted. It was solvable. It was solvable the wrong way. I got to the point where I saw the exploit and I was like, okay. And so, okay, there's two things though, dude. One is it technically fucking exploitable or not? Which is, of course, if it is, it's bad. Number 2 is it the goddamn sausage tower from Steven's Sausage Roll, which is the game quitting moment where even though there is an elegant, cool solution, because the level leads people to think it's like a grindy brute force solution, even if it's not possible, which in Steven's Sausage Roll it is, even if it's not possible, if people go for hours trying to do that, you're leading them into a grindy, unfun time and away from the point of the level. And so what I'm also trying to do here is clarify the point of the level, which is, look, you can't block the frickin' dragon. Now you still actually might technically somehow be able to get a 2-high block and then the warrior walks around. Except no, you can't, right? Because for the warrior to get out, they all have to be on the ground. So that's a thing that people can realize, right? And then they can also realize like, oh, he can't walk across. Once they're all on the ground, clearly he can't cross because he'll get fried. So he has to go around to the other end, and this is all deductible, right? Whereas in the previous version, those things were not deductible, and it it leads people into this unclear morass of horrible time, which I don't want to do. How would you open the door? The yellow door? Dude, people don't, like, even if it's not necessarily possible to line up all the stones again once you've messed them up, which I don't even know if it is or not, but let's say it isn't, it's hard for people to figure that out. It's really hard. And it's not the point of the level. Like, we want this level to be actually kind of clean. Like, here's the thing. There's a fucking 1,000 levels in this game. The longer each level is on average and the more of a slog it is, the more the game is just a long thing that goes on forever and you wish would fucking end. And we don't want it to feel like that. We want it to feel joyous and nice and like everything is cool and neat. And so the less confusing levels are, it's like, yes, I added a couple elements here. I added a dragon and a gate, but it actually clarifies the level for the player. And so even though there are more elements, it's better. Now, if I could figure out how to clarify the level for the player and also not have the dragon in the gate, that would be even better. Dragon in the fence. But I don't have an idea right now for how to do that. You just thought it was cleaner before. Yeah, well, that is, okay. So like cleanliness of the level or like lack of contrivance is an important thing that we optimize for. Absolutely. That is a good thing to look for. And yes, it is worse in some dimension to have a dragon and a fence there. That's 2 whole extra entity types than just a wall. A wall is way simpler and more elegant, right? But it has this other problem. So can I delete the blue button's door? And it doesn't change anything. Kind of, except I like part of what's neat about this level for me is this symmetry. Maybe it's fine though. Like, maybe it doesn't, like, I like this idea that this happened. Whoops. Just getting out of range. I like this idea that you do this slidey back and forth thing, right? And the blue buttons call that out. That said, maybe you should just observe that, right? Maybe you should just observe the cool sliding. That could be. And then maybe that's kind of, well, okay, no, it does change something. What it changes is you don't have to go all the way to the end, right? Like this. Now we could get rid of the horizontal blues and just leave that row of 5 or even a row of 3 there. That could be neat, right? Just leaving the row of 3. That would get rid of the initial symmetry, but it might make the level feel less intimidating and gross. Let's see. So yeah, again, I don't really know that we could get rid of all the blue. Like, it would change the level slightly, but that looks cleaner, right? So here, I didn't even know I was recording a test. So here, now, it's like I have to go all the way to the end anyway. And if I take away the blue buttons completely, which, to be fair, might be the right thing. It might actually be better. If I take them away completely, it's like I could get rid of that back wall and the blue force field. And then it's like, yeah, you don't have to invert the shape. I mean, we don't even need 3. We just need 1, right? Like, this would work just with this. That's kind of cool. I'm not sure whether I want to remove the button. Now the 3 with the stone stacks of 3 is misleading. Well, it's not necessarily. So the thing is, it's clear that you have to do the yellow first and then worry about the blue. And you need 1 stone on every yellow button. So there's no ambiguity about what you need to do. It's like you need to find a way to get these onto the yellow buttons, or you can't do anything, right? Okay, this is definitely a little better and more elegant. You know what? I could do this. Oh no, he would fall. So that's cute. Doesn't removing the blue door cause the player to think they can go to the other side before dropping down? That's true. It does reintroduce that ambiguity about, should I be manipulating those guys from the top? So maybe I like the blue gate for that reason. The symmetry with the yellow and blue buttons seems better. Yeah, maybe it is. Maybe it is. I actually maybe like this better. I don't know, though. It's not clear to me. It's not clear to me. Coke Zeros have caffeine. I was about to grab one, and then I was like, maybe caffeine at midnight is not. The 12 blue buttons win only on symmetry cuteness. I mean, maybe. Like, it does tell you... It does tell you the whole puzzle, but this version is in some sense more elegant, and it lets you observe the slidiness rather than being told the slidiness. Like, in terms of a puzzle designer aesthetic, this one's like the lightsaber rather than the blaster. You know what I mean, man? A little bit like that. Ah. You think get rid of the blue gate. I mean, the thing I don't like about that is, well, okay, we could get rid of the blue gate and just start the bar down at the bottom. Like, why am I so concerned with starting her at the top? You know what I'm saying? Like, what if we just do this? Okay. I mean, let's... Right? How's that? Oh, wait, we didn't start her in the right place. Because, like, the putting her up top... That's a kind of a flourish that I like to do, but like, maybe it's not helpful. Maybe, in fact, she could start at her exit. Because she's not hurting anybody from there, right? It's like, I could leave anytime I want, but I'm going to help my buddy here. That's what you said. Always put the bar on the bottom already. Yes, you did say that. You know, this maybe is better. This, I like this better already. Right, so we go here, here. This, if the other one, I liked it because it was elegant, then I have to like this one even more. So we do this, we do this. He gets, oh, but we don't, see, we don't have to walk to the edge. Like, all we have to do is go here. I kind of don't love that. I mean, maybe people could just have fun with it. Maybe that's fine. Right? Like, people could go and observe, and maybe that's fine. Move the exit to the edge. Oh. Then, yeah, that's a good idea. That's a good idea. I might have to give co-design credit to move the exit to the edge. Don't you already have co-design credit on a level or two? Let's start her on the exit again. I feel like I remember you contributing to a level before. All right. Timed recording. Boom, boom, boom. Boom, boom. I like that. I like it. It's a better level than it was. Now, that said, you are free after you put the warrior over here. You are free to actually kind of mess it up and get out, I think. Oh, maybe there's no way to mess it up once he's up there. Oh yeah, you could do this. You could like do a bunch of crap, but you're sort of encouraged just to go straight back. I think it's fine. You've helped other times, but you don't think... Well, whisper me your name, and I'll put you co-design on this one. Because that's a good suggestion. Can you put a couple of plants on the right platform? Well, when we do visual design of the level, we'll do all sorts of decorative things, but that's not what we're doing right here. Okay. I'm going to turn back on I-beam. I-beam 2 we'll think about later because it's bedtime probably. But I-beam 1 I think is better. I like making things better. It's so nice. Why do I have 8 whispers now? Who's whispering me on Twitch? Angry Bear 9 has whispered me 10 times. Maybe when he did a whisper, it like found all these old ones in the system that I hadn't seen for some reason. Yeah, here you are sending me level ideas 2.5 years ago that I don't know what that was about. Anyway, let me go into high security mode. So I don't dox people. All right. You now have co-design credit on this level. Assuming the level's in the game. If Zach like actually hates it for some reason and convinces me it's not good, it might not go in the game, but I like the level, and I think this version is much better than the original. Everyone's gonna kill the warrior on accident, yeah. Yeah. All right. Well, thank you everybody for coming by. We did programming. We did level design. We learned about sticking needles in your brain. I think that's like injecting bleach or something. We learned about all these things. We learned about Bitcoin going to $1 million. That was good. That was good. Thanks, everybody, and I will see you later.